Okay, so very well, welcome back. We continue now with the third and final lecture by Franco Flandoli. Is there? Okay.
Thank you very much. I hope I turn on this. Non lo sento, ma probabilmente sta funzionando. Ok, perfetto. So I hope the first slide helps to recall where we are. You remember yesterday we arrived to an equation which is the two-dimensional Euler equation in vorticity form, plus this additional term, which is of the same form of this transport, but here u is related to the velocity related to the vorticity. This dw over dt is a given stochastic process. W is like a Brownian motion, but with a dependence on x, which is summarized by the covariance matrix, or covariance two-point function. We understood that this is a sort of formal notation for something which, at the end of the story, contains a diffusive dissipative term plus an Ito term, which perfectly compensate into this Stratonovich integral, which has the same conservation law as the other transport terms, so any LP norm of omega is preserved if we don't have viscosity, but properly decomposed, reveals a potential dissipation if the Ito part is small in some sense. The Ito part cannot be small in the L2 norm, otherwise this would mean that omega itself in the L2 norm, the entropy, would decrease because of this dissipation, but the Ito part could be small in the sense like the mixing property, and so against test functions or in negative Sobolev topologies. And if it is small in negative Sobolev topologies, with proper handling of the nonlinearity, one can prove that also omega is dissipative in negative topology, which includes that velocity, which is like the h-1 norm of omega, is dissipative in the L2 topology, the velocity. So the energy, the L2 norm of velocity may dissipate. This is the summary of the story, but I started today with the understanding of when this Ito term is really small, and so the dissipation show up. Remember that the smallness, if any, comes from this coefficient epsilon q, which is defined here as the smallest coefficient, smallest numbers that Ma è andata alla fine? Come faccio? How do I how do I go to the beginning in 1 second? Is there a way? Otherwise I have to scroll. Okay. Thank you. Oops.
Adesso è successo qualcosa.
Sorry. Ok. No?
Magari vieni tu, Max.
Ecco, sì, grazie. L'ha fatto da là, guarda, fatto da là. È stato bravissimo da là. Grazie mille. Sorry, I don't know what I touched to produce that strange result. And so now we understand what makes this epsilon small in detail. it is, of course, a question of the choice of the sigma k. And before I describe this slide, you can start reading if you want, I can say the following, that I have in mind always two different families of sigma k. Just to make a comparison, but it's not serious, is like the dichotomy between Mikado and Beltrami. Here is a dichotomy between vortex structures and waves. When I think to the physics, I think to vortex structures. Vortex structures for me are compact support blobs of vorticity, which depending if we are in dimension 2 or 3, in dimension 2 are blobs with wings possibly, in dimension 3 are filaments, usually filaments, sometimes pancakes, but usually filaments. And if I think in terms of vortex structures, really I like to think to the fluid like a set of bodies which interact. Otherwise, there are waves. Waves are a little bit more abstract because, but there are waves in fluids. Maybe not these ones. Sometimes people observe waves in fluids. So these waves are a little bit abstract in a sense, but of course we know by Fourier analysis that at the end of the story they capture equally well certain aspects. And so now I use waves because tomorrow when I say a few words about convex integration in dimension 2, the point there was to choose between Mikado and Beltrami. Both of them don't exist in dimension 2 for certain reasons, but at least Beltrami, they have a counterpart of waves, which is the same. So I will use the same waves for convex integration. If I use vortex structures at the level of convex integration, nothing. At least, as far as I understand, nothing. And so I have to use waves today. Waves so means I take these vector fields, which are divergence-free because of the k-perp. The k-perpendicular makes that if you compute the divergence, there is a k scalar k-perp equals 0. And there are there is a small number and a large number. The small number is L stands for a length scale, very small length scale, because I think to very oscillating waves. So Ln is very small, and the wave numbers k are in a layer, a small layer around L minus 1. So you think in Fourier, if we are in, no, perché non l'ho preso? Okay. If we draw Z2, this is the origin, we are taking a layer at a distance L minus 1. Ln minus 1. N is the parameter which allows me to take a scaling limit in the noise, but you can think not to the scaling limit. Simply take a very small L and a very large, and the set of K is in a layer, in some layer of this form. So these sigma K are small because nu T is a constant, 1. Ln is small, but the frequency is high. Okay, this is just the same rewriting, just to say that you can write them as a sigma k depending on n, simply by the indicator function, because I use the notation sigma kn in some theorem. The covariance matrix, here, please pardon me, I should write this with sine and cosine, which is a mess, we don't understand anything more. So I use the complex notation, but if I use the complex notation, in computing the covariance matrix, I have to take the complex conjugate here, otherwise I produce the wrong result with respect to sine and cosine. And so think that here there is a complex conjugate which produces that the y becomes minus y, minus y, and so the covariance qxy becomes this one with x minus y, so it's a function of x minus y. You remember I already introduced sometime that the idea that sometime qxy is homogeneous, which corresponds to the fact that the noise as a random field is invariant by translation, namely invariant in law. The statistics of the noise are invariant by translations. They are equivalent to ask that this covariance function is depend only on the difference, is homogeneous. Now we go on. So in this covariance, you see there is a small number, a small coefficient, a large sum, because this sum is the... Oh, no, today I'm not very careful. I don't know why. So there is this sum is large. This set of wave numbers is very large, small coefficient. This is just a normalizing factor of tensor type to say is a sort of projection, and then the frequencies. To warm up, to understand the next result, I write, so first read only this line, which is extremely elementary. It means if you do the tensor and think that E1 and E2 are just the basis, the canonical basis of R2. If you do the tensor product of E1 with itself, of course, it is the matrix 1, 0, 0, 0. If you sum the other matrix with the one here, you get the identity. Okay, so remember that taking this sum of tensor products, you get the identity. And the same if you have many, like this beautiful picture. So I'm indebted to Ciro Campolina, a postdoc that grew up in the group of Alexei Malibayev at IMPA. Now Ciro is in Nice for the postdoc, and last week in Porquerolles, on the island of Porquerolles, we worked together, and he made this beautiful picture, so it's not mine. But tomorrow I will come back to this picture in a more substantial way. But today is just to say, instead of 2 vectors, you could have 8, and in this case, if you have 8 and you do the same sum, you get something like 4 times identity, okay? 4 times identity. Times the length of these vectors squared, or if you normalize the vectors, 4 times identity, okay? And this is the content of the next slide. Now we go back to our covariance with a huge sum over a small strip, and when we sum the same numbers like in the previous slide, but a huge number of them with the same kind of symmetry, because you have to, every time you sum 2 of them like that, you get an identity. And so you get a lot of identities in this sum, which compensate precisely with the factor ln, because the strip has essentially an area which is proportional to ln, and so you get a nu t. And so on the with this construction, I did this construction to have on the diagonal q constant, essentially constant. Of course, you can tune the constants before in order to have exactly equal to a constant if you want. So this is the point. Very small oscillations, but a huge number of them on this strip, they produce on the diagonal a constant. But when we go to this quadratic form, what happens? Okay, you take the q from here. Remember that qxy had in qxy there is an e2 pi I k x minus y. So you decompose the x minus y, one over vx and the other over vy. And you also decompose this tensor product against, because v is vector, so you decompose the tensor product against the vector v. and you get this identity. The factor comes out with the sum, and inside we have these objects, which are the Fourier components of the vector field in the basis of divergence-free fields. So in the space of, in the L2 space, so we take the space L2, usually people use this notation, L2 divergence-free. In this space, this is a complete orthonormal system, and these are the Fourier components of a vector field, which also I have to assume that belongs to this space. That belongs to this space. And so these are Fourier components, so the sum of the square of these Fourier components is less or equal than the norm of V. And so we see the final result is that we can keep the diagonal constant, not zero, and have the quadratic form as small as we like. As small as we like. So the Ito term, interpreted in a weak sense against test function, is as small as we like. If we do the computation in negative Sobolev spaces, it takes, written in form of slides, it would take 10 slides. At the end, the result is the same, a little bit less, much less clean, but the result is the same. Okay? Also with the negative topologies. And so we see that highly oscillating noise produce this kind of dissipation. This slide is more about a little summary and about tomorrow, but I decided to change the third and fourth lecture. So today I will speak about the three-dimensional case, where there is really a phenomenon of delay of blow-up, and I leave these heuristic comments about convex integration and so on to tomorrow. But let us read. So we have understood that highly oscillating fields with small in size, they produce a dissipation. I want to in a very imaginary way, I would say that is the fact that we use white noise is like to say that we use these fields, but we multiply very rapidly by plus minus 1. And the question is what happens if instead a sequence of plus 1 occurs, namely if we use the same fields but in a sort of bold way and not in this very nice way. What happens is a very difficult question, so don't expect tomorrow a precise answer, but the intuition is this one, that we have these fields randomized with respect to the field used, bold and not in the, I mean, very intelligent, but without randomization. Okay, but tomorrow. Today, let's restrict to the three-dimensional case. So I want to generalize the previous setup to the three dimensions. Maybe it's also better for pedagogically, namely, we have understood the torus T2, now we go to T3 and we try to see the differences. Okay? So Navier-Stokes in velocity is the same, but in vorticity it contains this additional let's use another color because it's a very dangerous term. Perché non lo prende? Ok, provo adesso. No, quello l'ho preso, perfetto, perfetto.
Adesso sì.
Benissimo, perfetto, grazie mille. Grazie mille. So this stretching term is, as all of us know, very dangerous. So the velocity field has a deformation which with eigenvalues, some positive, some negative, because the trace is zero. Typically there is two positive and one negative, if I'm not wrong, and then, but anyway, at least one positive, and this produces that the action on vectors is typically of elongating the vectors. And so this typically produces stretching of the vorticity fields. The vorticity field, at least in the turbulence, usually structures into vortex filaments. These vortex filaments are elongated by this tensor because of this positive eigenvalue. And even if the vorticity does not align with the direction of the positive eigenvalue, because you know when there is a positive eigenvalue, it produces increase in almost all directions except a few ones. So there is at least a little increase. Then since energy essentially should maintain, because when the vorticity increases, the energy, the vortex goes faster and faster, so the energy would increase a lot locally. So in order to prevent this increase, the vortex starts to fold, because when the vortex folds, the two arms of the vortex have rotate in an opposite direction, and so there is a depletion of energy. There is a depletion of energy. So in order to maintain an acceptable level of energy, there is folding. During this folding, if I understand well, there are bursts of diffusion. So the phenomena dynamically is extremely complex by this stretching. And in principle, if things are prepared in a careful way, this stretching perhaps could produce an infinite increase of the vorticity field. In principle, we don't know. We don't know when there is viscosity, at least we don't know. And let me summarize this difference in the Lie derivative just as a notation. So a notation which is useful sometimes because until now we had only this term. Now we have two terms, but think that this Lie derivative is the replacement of this term. So wherever until now we have seen the transport term, now you will see the Lie derivative. Just as a notation, but of course it's not the same. And so this is a very compact form of the Euler equation, of the Navier-Stokes equation in 3D vorticity form. And now we perform the same, okay, forse. Okay, perhaps I made a size which is incompatible with the shift. And so now we filter the vorticity and the associated velocity. These are the small scales, omega minus the filter, and this is the associated small scale velocities. We do the same computation as the first lecture, namely we filter the equation. So there is the Lie derivative acts on the large scales by means of the full velocity, which is a sum of large scale velocity and small scale velocity. But there is a commutator. Then let us delay the commutator, even more difficult to accept the idea that this commutator is small, but let's delay this commutator and study a new mathematical problem to see what we understand from that. So it is I delete also bar because this is a new mathematical problem. I have a vorticity field transported by its own velocity u, but also by another velocity field u prime. This u prime is understood as something very small scale, very rapidly oscillating, which adds to the self mechanisms. Okay, so this is our starting point. And Next step, idealize. So we idealize U prime. So this, if you want, this is a summary of what we did in the last lectures. We idealize U prime into a noise. So at the end of the story, this is the equation I want to study next. Okay? If you want, is the classical Euler or Navier-Stokes equation in 3D with an additional term coming from small scales. But this reconstruction that is the same as previous lectures is fundamental to point to observe that the additional term which describes the action of small scales on the larger ones is of Lie type, Lie derivative type. Let us see more clearly this. I rewrite this equation here and expand the equation. So this is the same equation expanded. So the self is self-transport and self-stretching, but also the noise is random transport and random stretching. So not only there is the self-stretching, which we know is very dangerous, but there is also the random stretching. And unfortunately, in the last, it's around 2 years that I work on this topic, and in 2 years I've not understood what is going on to this random stretching. I think it's a difficult question because analogous questions are treated if you delete, let me take a very light green and delete this part. If we delete this part and we replace omega by m or b, this is the equation for a passive magnetic field activated by noise, which is a topic which is studied for the purpose of understanding the dynamo effect, the fact that magnetic field could strongly erase somewhere, and understanding the self-stretching. The stretching by the noise is really very difficult. So in this equation I've not understood it. Or at least what I have understood is negative, unfortunately, namely that my computation stops somewhere. I will come back to this point. And so since I want to show a theorem, I have to make something artificial, namely delete this term, not this one. I keep Navier-Stokes Euler. I keep this. I don't go to the magnetic field. This was just a remark. So just a remark to say that there is this additional difficulty of Euler, but even for the magnetic field already, which is a linear equation, this is extremely difficult. So, but let's go back to our Euler equation. We go back to the Euler equation. It's better to erase it to avoid misunderstandings. I go back to the Euler equation. And for the Euler equation, I need to delete this term in order to be able to say something. So the model I'm going to describe, unfortunately, is artificial from the viewpoint of physics. In the paper that we published, we wrote this very clearly in the 2 pages of introduction to explain that it's absolutely artificial. We don't want to hide this very important detail. Absolutely artificial. So I will delete this. Of course, this slide speaks of variants. There are simplified variants of the 3-dimensional setup. One of them, for instance, thin layers, etc. One of them is Taylor-Proudman. It's a model in which there is an invariance with respect to a vertical component. It's still a 3-dimensional model with a certain invariant with respect to the vertical component, which makes a simplification. In that case, we can keep the stretching term and we can prove completely our theorems. Unfortunately, these theorems are not a regularization by noise because Taylor-Proudman is already well posed. So if we move to 3-dimensional variants, which are already well posed, like Taylor-Proudman, we can include the random stretching and treat it up to the end and show that there is an additional dissipation. This, even if there is the random stretching, this noise, which now is random transport and random stretching, produces an additional dissipation in the Taylor-Proudman. It's not regularization by noise because the equation is already well posed. This is the point. So let me stay at the fully three-dimensional level, not a Taylor-Proudman, this is just a remark, fully three-dimensional case, but without this, because I don't know how to treat. The philosophy, but let me, before I move the slide, the philosophy behind the Taylor-Proudman at the end of the story is the following. Perhaps one can do something in 3D if the geometry of the noise and the vector field is suitable. So if there is a suitable interplay of the geometry of this noise and the field, maybe something can be done. I don't know if locally in space, when there is a huge vortex, this has sufficient time, because if you produce artificially a strong rotation to the full fluid, what I'm going to say happens. The problem is whether it happens locally in space and locally in time, because it's a very fast process. So if locally in space and time, a huge vortex producing a strong rotation creates in the surrounding the effects of strong rotation, then maybe the mathematics of Taylor-Proudman can be applied locally in space and time. Globally it works. So globally strong rotation produces some geometry of the small scales with respect to the larger scales, which is in the correct direction. Locally in space and time is a question of speed of the processes, and I don't know. Turbulence, I mean, if there is a sufficient separation of scales, maybe it works, but I don't know. So this is a mystery. The understanding this stretching term is a mystery about which I have some idea, but I don't know. Sorry if I made some complicated heuristic comments. That is not so easy. Just since I said something that probably is pedagogically not very clear. When you have a very strong rotation, there is a tendency of the structures, of the small vortex structures, to align in the vertical direction. This is observed in experiments, fluid experiments. If you produce a strong rotation, there are columns of the small scale vortex structure create columns in the vertical direction, roughly speaking. And so the idea is, assume you have a huge vortex at a large scale, which has a tendency to blow up. So we are looking for the problem of blow up. So this vortex tends to increase, to become thinner and thinner and longer, and faster, and move faster and faster. So it's in the direction of blow up. Maybe locally it produces that the small scale structures align to it, and this geometry is compatible with Proudman-Taylor. This is what I wanted to say. But the time it needs the strong rotation to create these columns is the critical issue, one of the critical issues that I have no idea if there is sufficient time. These processes are fast, but I don't know if they are sufficiently fast. Okay, let's go back now to our artificial model. The artificial model is with self-transport and self-stretching, but only random transport. However, written like that is not correct, is incorrect, because there is no balance, because all terms except this one are divergence-free. The other terms are divergence-free, but this one is not divergence-free. And so this equation has no solutions, because if U is a solution, there is a contradiction, 0 equal 1. And therefore, we have to project. So we have to take the same, sorry, here there is a theorem. We have to take the same model with self-transport and self-stretching, and the transport noise is projected. This P stands for the projection on divergence-free fields. Okay, this equation is locally well posed. So if you, okay, maybe there is also a weak global results, but I'm looking for regular solutions. So I take initial vorticity L2. I studied this equation in the class when the initial vorticity is L2. Initial vorticity L2 is like a velocity h1, which is outside the weak solutions. It's already in classes of smooth solutions. And for this class of smooth solution, local existence and maximal existence is a classical result without noise and with noise. So this noise with projection is compatible with the basic mathematics. The point is that there is this additional theorem. You can prescribe a size of the initial condition, R0, and unfortunately you have to throw away a little bit of realizations. Prescribing these two numbers, I can exhibit a noise with the property that for every initial condition like that, the time of blow-up is infinite. So there is no blow-up in the L2 norm, up to this small set of realizations. So the blow-up is prevented by this noise in this particular sense, up to a small probability. And not uniformly in the initial conditions, in all initial conditions, but for all initial conditions in a given ball. So I can prescribe this ball very large, find a noise such that. This is the result. This is the best, to my knowledge, I mean, no, to say the best is wrong. It's the only result of regularization by noise for 3D Navier-Stokes equation. So let me repeat, unrealistic from the physical viewpoint, with drawbacks like this epsilon, etc., but it is an indication that maybe there exists regularization by noise for the three-dimensional Navier-Stokes equation, completely different from the principles based on additive noise. And the regularization is not restoring uniqueness, but is preventing blow-up. So this change of mind that I described in the last lectures. For the 2D case, the analog of this does not exist because in 2D there is no explosion. So this is why in 2D I described the results in detail in 2D, but at the end of the story it was just an additional dissipation, not an additional well-posedness. In 3D is an additional well-posedness.
But sorry, can I ask you if in 2D but with fractional diffusion? Because in any case the diffusion, I mean, you could consider fractional diffusion in 2D, no? Navier-Stokes is critical.
I admit that I didn't think about that. The point is that this kind of noise, Brownian, always is associated to a Laplacian, so it would perturb your fractional problem by an additional Laplacian term, so very strong, very much in the direction of well-posedness. So I suspect I didn't think to this question. Right. No, fractional Brownian motion, no. I will, if you wanted to, I prepare a slide for tomorrow. Fractional Brownian motion is tremendous. It produces something like Laplacians with a power of t in front, like 2h minus 1. So if you take a fractional Brownian motion with as parameter greater than 1/2, the effect is less dissipative than Brownian motion. So maybe it regularizes, but there is a problem that the coefficient in front of the Laplacian is infinitesimal for small time. So I don't know. So fractional random motion could have trouble. The one that could be comparable are Levy processes, so alpha stable processes. So with an alpha stable noise, you can create a fractional Laplacian, and so you could compete with the right fractional. So take your problem with the fractional Laplacian. If you put white noise, in a sense, is not is unfair. Well, you enter with a Laplacian into the problem. If you take an alpha stable process with the right alpha, you can create a fractional Laplacian of the same order and try to make some theorem. Perhaps. However, the theory with fractional Laplacian is completely different, and namely it requires the concept of Stratonovich for sorry, not fractional Laplacian, the alpha stable noise requires the Stratonovich, the analogous of the Stratonovich is the so-called Marcus, I thought Markov, no, it's not Markov, it's Marcus integrals, and there are very few papers on that. I know some friends, Zizek, Brezniak, and others that are working on Marcus integrals for transport equation, linear transport with noise. So perhaps in the next future there will be the mathematics available on this topic. Okay, I didn't think about that. Thank you. Very good. Very good. C'è un problema? Ah, ok, sì, ok, d'accordo. Okay. So let me give a few elements about this topic, this theorem. I don't give the full proof. The full proof is, not so difficult but very long, because we had to mollify the nonlinearity and use stopping times, etc., etc. So ideally, the proof is the following in few slides. But first a remark on the deterministic case. So, remark on the deterministic case: if you start with L2 vorticity, locally, I already said, locally you have a solution unique with L2 vorticity up to a time which is not random. I'm talking about the deterministic case, and but maybe there is a blow up. Maybe the time is finite, and the limit of the L2 norm of vorticity is plus infinity, and we don't know. This is a version of the $1 million problem. And what yes, and always in a deterministic case, let me show the following computation to understand very clearly which is the point of our strategy. But deterministic. So deterministic 3D Euler, vorticity form, take usual energy estimate, and the point is to handle the stretching, this form which corresponds to stretching. And this form is bounded by the L3 norm of the vorticity, because gradient of u is, like vorticity from the viewpoint of function spaces, and L3, and then use Sobolev embedding, and then use interpolation. What is this? Yes, this is interpolation, because this is Sobolev embedding with the level of differentiability 1/2, and here is the level of differentiability 1. So this is interpolation inequality, and then trivial inequality. And so at the end of this very classical bounds, we see I preserved a nu with the W12 topology, because I have this term on this side, and unfortunately there is the L2 norm of omega to some power. With this computation the power is 6 divided by the viscosity cube. So at the end this is essentially the inequality for the L2 norm of the vorticity, for the entropy, and this only provides a local control. This is a classical deterministic computation. One can do it maybe better, but this gives the correct idea in a sense. And the key remark, so the first remark, of course, is that it provides only a local control in time. But the second key remark, I hope, is written here. Is written here compared to this inequality. If the viscosity is larger, of course, the time on which we have a control is longer. So the length of the interval of time on which this inequality produces a control is larger for larger viscosity. Absolutely natural. Simply I wanted to have it with mathematics under our eyes. And therefore, you understand, since the transport noise improves the viscosity, improves the time. It's even true, with more arguments, that if the viscosity is sufficiently large, with another additional argument, if the viscosity is sufficiently large, the solution is global. So it's global. And so, depending on the initial condition, if you prescribe the size of the initial condition, you can find a threshold of the viscosity that above the threshold, not only this time interval is increased, but it becomes infinite. The threshold depends on the size of the initial condition. And then you understand, since our noise, we understood from the two-dimensional case, provides an additional dissipation, clearly it increases nu. Here there is a theorem which is like the theorem that I already stated, but perhaps a little bit more quantitative and explicit. It says that if we take, I can construct noise with a scaling limit. It is in the next slides. In the next slides I will write the noise explicitly. I can construct a noise and take a scaling limit such that the limit equation of my 3D Navier-Stokes with only transport noise is this deterministic 3D Navier-Stokes, in which the old viscosity is increased by a turbulent viscosity. This factor 3/5, I could of course hide this factor in the turbulent viscosity and say there is an addition. But the point is that there is really a 3/5 emerging from the computations, which is curious, and so I want to emphasize later this detail, opposite to the two-dimensional case. And the convergence of the stochastic equation to this deterministic, exactly like in the two-dimensional case, is in a negative Sobolev topology. However, for this Navier-Stokes equation, this slightly negative Sobolev topology is sufficient for the arguments of well-posedness, etc. So it's like working in L2, essentially, from the viewpoint of... and so the convergence in this negative topology is sufficient to map back the estimates for this problem to the stochastic. Because this problem, due to the increased viscosity, has additional estimates. Thanks to this additional viscosity, the deterministic problem has additional estimates. These additional estimates are mapped back to the stochastic problem because the stochastic and the deterministic are close each other in this topology, not in L2, in this topology. So the stochastic problem has additional estimates in this topology, thanks to this twin, additional estimates in this topology, and the additional estimates in this topology for small delta are sufficient to have global well-posedness. This is the intuitive idea, similar to other fields, like, for instance, I like the activity of Babin, Nikolaenko, and Makhalov, in which they proved that under strong rotation, the 3D Navier-Stokes is well-posed, because similarly it converges to a model which is like 2D with better estimates. The better estimates of the limit move back to the other. And also in that case, they have to use vorticity, because pay attention, if you do the same trick at the level of velocity, it doesn't work, because if you do the same kind of strategy at the level of velocity, you have a closeness between the stochastic model and the limit deterministic Navier-Stokes in velocity in topologies like H minus delta. And H minus delta in velocity is not sufficient to increase the informations. So it's very important to work with vorticity,
Why
because
don't you get H1 minus delta in that case? I mean, why don't you get the same space?
Sorry, I understand your question. So it is due to a misunderstanding. Let me expand a little bit. There are two really different. It's not just a question of names. Two different strategies of regularization by noise, namely to put the transport noise on the vorticity or the transport noise on the velocity. So it's not a question just of using the name velocity instead of the name vorticity, but really to use two different noises. One
Vorticity is strong.
Is strong because put the noise. This noise, as I said once, is vorticity preserving. This transport noise is vorticity preserving. If you put a noise which is velocity preserving on the velocity, you have a good bounce and convergence in the velocity, but unfortunately in a negative topology for the velocity, and it's not good enough for improvement of well-posedness. So it's very important to do it at the level of vorticity.
Yeah, it's important how nu t depends on t or not.
Sorry, this T is not a capital T.
No,
I didn't notice. This T is from Boussinesq, is turbulent viscosity. This is a tribute to Boussinesq, and this is capital T, so it has nothing to do.
So nu t does not depend on the interval in which you work?
No, it does not depend. We will see the noise in a second. It does not depend. It depends only on the vector fields that I choose in the noise. Okay. No, this is independent. Yes, sorry, this is a complete misunderstanding. Delete this T and don't put mind into the fact that this additional viscosity could be related to time. Sorry. Okay, we will see the noise in a second because. Yes.
No,
right.
I mean, I don't understand the mechanism. In the end, I mean, you end up on an equation which is like the previous one with a bigger viscosity.
Right.
Can you explain again, I mean, what is the key to prevent blow-up at this point? Because this can have blow-up, no?
Yes, but if given an initial condition, if this additional nu is large enough, this has no blow-up anymore.
Because the nu, okay, you fix an initial condition and then.
And then, but it's sufficient to fix the size. This is written in a poor way. It's sufficient to fix the size of the initial condition. So if you prescribe the size of the initial condition, you can find a noise which gives you a constant sufficiently large to prevent blow-up of all initial conditions with that size.
Okay.
Increasing viscosity increases the length of maximal existence in principle.
Yes.
But over a threshold, you don't blow up anymore because
sure.
it's like just to have it's like the equation x point equal x square. If you stay below 1, the x square is
Sorry,
it's not
because t is fixed. I mean,
right.
at that point is that here the time interval is fixed.
After a while, you stay over a threshold that your solution. I mean, the nonlinearity. Your solution is so small with respect to the nonlinearity that the nonlinearity makes it even smaller. But it depends on the. Sorry. I cannot explain. I should think.
No, I mean, an equation like that has an existence time. And which depends on m in the right,
right, but which is the example? Sorry, I'm thinking to the example that it is blow up over 1, but not below 1. Is minus x is perhaps this one. If you start above 1, this is 0. This is 1. If you start above 1 due to the square, you blow up. If you start below 1, you stay trapped inside here. And this idea is the same, more or less the same why if you have sufficiently large viscosity, you never blow up. It's not just a question of increasing the length of interval, but you go to plus infinity.
Okay, so the same theorem would be true for t equal infinity?
Yes, yes, yes. So this is, in fact, this is not equivalent to the previous theorem. It's just an intermediate statement in the paper, which, but I wanted to write because it makes very explicit which is the limit deterministic equation, the topology, etc. But so perhaps I should write better. Yes, yes, you are right. I was not careful. Essentially, you can delete this sentence, but in doing the proof, we first did on a finite time, and then we enlarged by another argument. So this is an intermediate statement. Okay, I hope. Certainly there is something unclear, but there is always something not clear in my presentation that in the papers I hope is more clear. In order to prove such theorem, we need to understand the structure of the noise, and this is something I will describe. There is a difficulty concerning the Ito-Stratonovich corrector that I want to emphasize, and then I don't want to enter into the Sobolev estimates of the Ito integral. I showed you the estimates of the Ito integral against S function. Let's decide that we are satisfied with that as an intuition. And when you have the Sobolev estimates in negative spaces and you use the Navier-Stokes carefully, you also have a control on the solution in these spaces. And I don't do that. So step 3, I don't discuss. I leave it to your intuition that based on what we learned, we can do this. This is in a sense, this is the longest part. The longest part, but is machinery of 3D Navier-Stokes and machinery of stochastic analysis. I want to discuss the noise and the Ito-Stratonovich corrector because there are curiosities. So first, about the Ito-Stratonovich corrector, let me say the following. We have a deterministic equation plus a Stratonovich term. This Stratonovich term can be written as an Ito plus a correction, and this we already know from the previous lecture. What I didn't show you is that this can be done in general, even if the shape of this Stratonovich is not exactly like this, in general, and the final general result is that this corrector is always of the same shape. This corrector is 1/2 if the noise is defined, if the noise is a sum of noises, the sum appears. And then the linear operator written here, this linear if we call this L of omega, L is not the Lie derivative here, is just linear operator on omega. This linear operator appears iterated. So this is the general shape of the Ito corrector is 1/2 sum of LK omega. LK. So whatever is this linear operator, when you move from Stratonovich to Ito, simply, Ito is Ito, not against Stratonovich. So Ito is just the same integration, but in the Ito sense. And this corrector has this shape. So now the problem is that without these projectors, this expression is very nice. Without the projector, let me, with another color, maybe let me show. If we don't have the projector, if we have only the sum over k of sigma k gradient of sigma k gradient of omega, so if we iterate the operator sigma k gradient, since sigma k is divergence free, I can put inside and write this as sum over k of divergence of sigma k tensor sigma k gradient with more brackets, but let me leave it here. And then the sum of the sigma k is the q divergence q gradient. The q computed only at x, only on the diagonal q xx on the diagonal gradient of omega. But with this projection, which are non-local operator, everything is wasted. So unfortunately, one of the main difficulties of this research was to understand this Ito-Stratonovich corrector due to the non-local operators. At the end, my colleague Hyunju Know, not me, understood it, and fortunately we had a final result. So this is a key technical difficulty.
But in the end, what do you need on this operator?
Because the problem is whether the limit, yes, thank you for this very deep question. You need that it adds dissipation. Maybe it could be a non-local operator which improves dissipation. This could have been a possibility. Fortunately, it is a Laplacian. Fortunately, in our scaling limit, this converges to a Laplacian, so the non-local part disappears in the limit. If the non-local part would be maintained in the limit, we should have analyzed if this non-local operator still increases the dissipation of delta. But Hyunju Know was able to prove that because we have a sequence sigma n, in the limit of this sequence, he was able to prove that this converges to a Laplacian, but with the factor 3/5 in front that I showed. I will show it is stated in one of the next slides. For now on, sorry if I had to answer. I make a lot of comments that probably are difficult to understand immediately. But the point is, the Ito-Stratonovich corrector is not as easy as usual. Fortunately, it becomes again easy, like a Laplacian, in the scaling limit when n goes to infinity. This is the message. But requires work. So this is just rewritten. And this is the computation that I just wrote by hand. So this slide you already know. The noise, let me show, I'm almost at the end, which is, but let me check that I'm not out of time. There is time. Yes, following the advice of Daniele, I kept my slide to 24 exactly. No, ciao, non ti ho visto. So the noise. The noise is more or less the same that I have used in 2D. In 2D, simply here is written more carefully with sine and cosine. So the frequencies are given by this sine and cosine. The vector structure with the proper orthogonalities are given by these vectors, which for every frequency k, since we are in 3D, for every frequency k, you need two vectors. These two vectors that together with k, normalized k, they are an orthonormal basis. And so you have, because you remember in 2D we had only one vector, k perp over k times e to the power. So this was sufficient to build the complete orthonormal system. In 3D, you need for each one of this object, you need two of these vectors, not only one. And these two are just two orthogonal vectors. And so this makes more complicated the shape of things. So these are two vectors orthogonal to k. Not only one vector orthogonal to k. Apart from that detail, the sigma k that appear in the noise now depends on k, and this index alpha, which is just 1 and 2. somewhere should be written that alpha is just 1 or 2, so there are two indices. These sigma k are these vectors times a constant which will be chosen to tune, for instance, copying the philosophy of the two-dimensional case, this constant will be small. We want small, fast oscillation. But the smallness must be tuned carefully because we still want to preserve that the diagonal is not small. And so we cannot just take this infinitely small just to destroy the Ito term because we want to maintain the diagonal. And so we have to choose these coefficients carefully. We choose them invariant by rotation, so everything is made isotropic. And here is the quantitative result without the projections. So this quantitative result is not the one we can use, because unfortunately we have these projections in the in the corrector, Ito-Stratonci corrector, we have this projection twice. Here is written without the projector, but this lemma clarifies how big the theta must be. And so to understand what kind of oscillation we need, we understand in this sort of easy case, which is not our case. Then when we have the projector, we use the same and we fight against the projector. Okay, this is the point. And so the idea here is that in Fourier, in Z3, without 0, we take like in 2D. Here, for minor reasons, instead of taking a thin strip again around a level, I took this. Probably because in the paper we wrote that, and then I kept the notation of the paper. So we take the wave numbers in this strip, but you see between n and 2n. So there is a scaling parameter n in the problem. This is the scaling parameter which goes to infinity, and n is precisely this. And so the wave, so the oscillations are at these frequencies, and in front of the oscillations, I'm sorry that I put this blue over, but I think it's still readable, that this theta, which are the same, are invariant by rotation. These theta are invariant by rotation, and I take theta independent, just the same. In this annulus, the theta have the same value. The same value is written here: square root of viscosity, like in the two-dimensional case, and a certain power, a suitable power of the scaling parameter. That in the two-dimensional case was a power related to the two-dimensionality and the fact that I took this strip very thin, and here is another number related to the fact that I took 3 dimensions and I took a strip with a certain size, but is something, there is a minus, so I'm sorry that here is not visible. What is written here is n to the minus 3/2. So it is a small coefficient, so very small, fast oscillations. Okay, for people who knows convex integrations, they sound familiar. Very small, fast oscillations. And with these choices, what we get? With these choices, we get that the diagonal. This is QXX. This is QXX. The diagonal is like the L2 norm of this family of theta, and the L2 norm of this family of theta is constant. If you sum these numbers on this set, you find the constant. So the additional Boussinesque turbulent viscosity is a constant. At the same time, due to the fact that these theta are small, when we compute the quantity epsilon that you remember, when we compute the quadratic form is is very small. Just recall that the previous slide is concerned with this simplified corrector, which is not our corrector. We have to understand our corrector. Probably, if I remember well, I just gave a few information on that because it's very long. In order to understand, so we have to compare our corrector, which includes the non-local. This part is a little bit boring, but since it is mysterious, I want to add at least 2 or 3 slides. I remember that every time this is discussed, also for myself, is a little bit mysterious. So I didn't want to completely to hide and say the result is the same. So when you have this corrector with the non-local terms inside, we want to compare with the corrector without the non-local, the classical corrector of the 2-dimensional. This is the corrector of the 2-dimensional case. And this is the corrector in this special 3-dimensional case with projector. And we do, if you do it at the level of quadratic forms, it becomes a little bit more transparent because you can express, you can do the following. You can express the classical corrector by means of the projected one in this way, to decompose the classical in 2 quadratic form, one with the projected and one with the orthogonal projected. And maybe from this you start to believe that in some sense they contribute to pieces of this one in the limit. And this is what we prove. I decided not to put another 5 slides of proof of this, otherwise the slides would become 24 plus 5. And so I end up with this lemma. This lemma states precisely that these 2 non-local quadratic forms converge to proportions of this easy quadratic form in the limit. In particular, the corrector that we are interested in the weak sense, converges to the classical one, but only a proportion of it. There is another proportion lost along the story, of which I didn't find a beautiful physical interpretation, but this is the result. So, to summarize, in the talk, I completed something about the proof in the 2-dimensional case, highlighting the importance of this fast oscillation, small intensity, which works. And then, essentially, I repeated step by step the same in 3D. Unfortunately, really step by step, in the sense that in 2D there was the transport noise, and I take the transport noise in 3D, which is not physically correct. But it's the only thing I can do today. I repeat, and it works also in 3D, providing a result of a result. And together, let's say, if we put together these results with the no collision theorem for point vortices that we have seen another time, at the end, even if I already said many times, let me say again, there is perhaps a regularization power of the transport noise, but in terms of blow-up. For the linear transport equation, it was a regularization power in terms of uniqueness, but for nonlinear problems, it seems in terms of blow-up. Whether this is deep or so is still something we try to understand, I think, is the end. Thank you very much.
Thanks, Franco.
Thank you.
So we have time for questions. Okay.
So maybe I have a very naive one. Does it have any physical meaning to relate the small scales of the noise and the viscosity nu you have in front?
Okay, this was predicted by Boussinesq in so Boussinesq in 1875. If 76, if I'm not wrong. So Buzinescu understood this a lot of time ago. So he had the feeling that in a turbulent, if there is a turbulent, so fluids usually contain large scales, like think to a wind tunnel. There is the large scale fluid which moves, and turbulence provoked, for instance, by a grid, artificially provoked by a grid or by a surface of a car or an airplane in the experiments of the wind tunnels. And he understood that the small scales of the turbulence could produce an extra viscosity or dissipation of the fluid. And this is observed in many real-life cases. For instance, we all heard that inside the pipes, if you succeed to move the fluids inside the pipe in a laminar way, it's much better, because otherwise, if the fluid in a pipe becomes turbulent, it goes slower and dissipates more at the boundary, more heat. So unfortunately, due to turbulence, when we heat and we make the shower in another room, a lot of heat is lost along the street. If the fluid was laminar, we would lose much less heat in the pipe because essentially there is a laminar profile like that. Sorry, a laminar profile like that, and a turbulent profile which is like that, and the derivative of the boundary is the coefficient, is the quantity which describes the drag of the fluid, and also the dissipation, the Nusselt number, the dissipation of the fluid in terms of heat. So a lot of technological facts depend on the problem that turbulence provokes an increase. There is, in this case, an increase of both this and both the coefficients of viscosity and dissipation of the fluid. And this is a phenomenon that is completely true. Unfortunately, the mathematical description of this phenomenon that is usually done by the models called the large eddy simulation, in which they add, is unclear. Namely, in large eddy simulation, they have the Laplacian, and they add an artificial term. Sorry, it's done in velocity. Usually, it's done in velocity more classically. Okay, here there is also velocity. And the problem is what to put here, and this is a bigger problem. So the point is the fact that this phenomena corresponds to a Laplacian. This is very unclear, also experimentally. The fact that turbulence produces an increase of viscosity and heat coefficient is absolutely common, absolutely common. What is not clear is whether we can describe by Laplacian in a full sense. For instance, maybe many of you know the Smagorinsky, for instance, said that this coefficient should depend on. So there are many practical rules by engineers about what is the correct correction instead of the Laplacian that I used in the previous slides. But the idea is clear from that. From the engineering point of view, is absolutely clear.
Some more questions?
So you mentioned that maybe one way to understand how to put the stretching term in is to, if you just study the vector advection equation, sort of in the context of the dynamo problem you mentioned. And you know, one of the things that I remember learning about this is that if you have something, let's say a flow which is behaving more in a planar sort of way, the loops fold onto themselves, and you always have anti-alignment of the vorticity. And so the mixing effect somehow causes rapid vortex depletion, and you don't get this sort of unbounded stretching. But if you really have three-dimensionality and you have lots of twists, in the loops, then when they fold together, they line up with each other, and you get explosive growth that is probably going to be the problem that you're fighting. Do you think maybe there are some very specially constructed noises you can make that sort of, they have geometry that really only sort of perturbs in planar ways?
I completely agree. Is precisely my. I will ask you the references that you have seen because probably I don't know them, but is precisely my view. If you use isotropic turbulence, it doesn't work. We have estimates, unfortunately, with an upper bound, so we cannot say that they don't work. But the upper bound seems to be almost correct, almost an equality. And if it is an equality, it doesn't work. Isotropic turbulence presumably doesn't work, doesn't produce the same. But if the turbulent part is sufficiently two-dimensional, in a sense, it is precisely the model that I mentioned, Taylor-Proudman, is precisely like that. It's a sort of two-dimensional turbulence acting on three-dimensional vectors. But the simplification of that model is not only the noise, it's also the velocity field of the fluid is invariant by vertical coordinate. Only thanks to this invariance we can close the proof. It's interesting that if in that case we find the additional Laplacian plus another term, a first order term, let me say A grad omega, which is called the Aka term by physicists because the physicists already understood everything, but they call the Aka term. So in the Taylor-Proudman model, we understand that the corrector, the Ito-Stratonovich corrector, is not only a Laplacian. It could include a first order term depending if the noise has a property called mirror symmetry or not. And so this Aka term in the case of passive magnetic sometimes is thought to be the origin of the dynamo effect, by the way. So maybe I think that in 3D there are a lot of things that in the future some people will understand about the geometry. But I completely agree with your comment.
More questions, comments? Okay, so if not, we thank Franco again, and we have a coffee break until 11. Okay, so welcome back. We can continue with the third lecture from Professor Albritton. Thank you.
Thanks. Okay, so maybe I'll stand for now. So last time we explained two mechanisms for obtaining non-uniqueness using self-similar solutions. The first one was when you have some kind of bifurcation in or from the class of self-similar solutions. So you might get something like 3 self-similar solutions from the same self-similar initial data. And then we ended by talking about how if you have one self-similar solution which is unstable, then when you construct the unstable manifold in self-similarity variables, that gives you a non-uniqueness proof. So we left open the question of how do you actually find these unstable self-similar solutions, and that's what we're going to talk about today. And we're going to actually consider them perturbatively from unstable steady states. And so we're mostly going to talk about unstable steady states, and we're going to do some classic calculation from Rayleigh in the 1800s about shear flows, just to kind of give you some idea what goes into of what's going on. So we left open the question. Okay. All right. How to find an unstable self-similar solution. So I'm going to talk a little bit about Euler. I'm going to switch from the Navier-Stokes setting and talk about Euler, and it gives me a chance to talk about Misha Vishik's work. So basically, all right, so it's known if you're considering Euler, incompressible Euler, then in any dimension, all right, let's write Euler. So this is in any dimension, and then we can also, we can write vorticity form. So let me just write the two-dimensional version. So we write 2D Euler. So remember, 2D Euler is a transport equation for the vorticity. And the vorticity is the scalar, in 2D it's the scalar curl of the velocity. And you close these equations first by recovering the stream function from the vorticity. So Laplace psi equals omega. And finally, U is grad perp of psi. So Euler is well posed in for velocity in C1 alpha. Okay, so if you have U naught in C1 alpha, all right. So Euler is well posed. I mean, that goes back to Liechtenstein in 1910s or something. So you could also say, you could also think, I put my vorticity in C0 alpha, and you want to make sure your velocity has finite energy in order to control large scales. This would also, you would also be able to prove, well posedness in this class, and that holds in any dimension. Okay, in 2D, vorticity in bounded vorticity is a uniqueness class. So 2D, if you assume, let's say vorticity is bounded, and let me also put it in L1. Okay, the key point is really L infinity, and let's also assume that the velocity has finite energy. But this is really just to control large scales. So the key point is really this L infinity here. Then Euler is also well posed in this class. Okay. So Euler is also well posed. Because 2D Euler is a transport equation for the vorticity, you have a maximum principle for, you in fact have conservation of L infinity norm of the vorticity. And by Biel-Kato-Maeda, you know that if the solution blows up, L infinity of vorticity must blow up. So this gives you that 2D Euler is globally well posed in class of bounded vorticity. Okay, with some other, maybe with some other background conditions like this one or this one. And okay, this essentially, this is due to Udovich. So on the other hand, if you just have LP vorticity, you can find weak solutions of 2D Euler. This is a transport equation for vorticity. LP norms will be conserved, and that gives you enough. That gives you enough compactness to make sense of the velocity equation. And you can find. So on the other hand, you can find weak solutions with bounded or with vorticity, which is just LP. Okay. On the other hand, if you just have vorticity in LP, and maybe some of these background conditions, then there exists global and time weak solutions, global weak solutions. And you might just ask the question, are they unique? That seems like a reasonable question. You can find the weak solutions, are they unique? So, question, are they unique? And, okay, answer. By Bresson, Murray, and Shen. Probably no. By probably no, I mean that there are numerical simulations which very strongly suggest that there are multiple self-similar solutions coming from LP initial vorticity, coming from the same initial vorticity in LP. And so, okay, so the answer is probably no, but it's essentially currently at the level of this geospheric bifurcation stuff. There's numerical evidence and no proof. On the other hand, if you let yourself work in the forced class, so you study this equation, equals now curl of some body force. Now, where should this live? You want this to be at least in L1 time LP. And then you can also find, if you solve this equation, you can also find global weak solutions. And you can ask whether those are unique. Okay, so in this equation, you still have global weak solutions. Put the background assumptions, finite energy, things like that. Are they unique? And so the theorem by Misha Vishik, 2018, is no. Okay. So I guess I could say more than that, which is like, you could say like, for every p less than infinity, you can find a force such that that there exists two distinct finite energy weak solutions of the Euler equations. But that's just the long version of this no. Okay. So we wrote lecture notes on these papers, and I'm going to give you a flavor of what's going on in them. Okay. In 2021, we wrote lecture notes with, myself, Elia, that's the B, Maria, that's the C, Camila Delelis, that's the D, Vikram Giri, who also appeared in Gianluca Crippa's talk, he's the G. Maximilian Janisch, he was a master's student of Camilo at the time, he's the J. And Hyunju. Okay, so these lecture notes emerged out of a reading seminar that we had at the IAS, which started in November 2020 during COVID. And it was really a big relief because it was one of the only in-person mathematical experiences. It was the only in-person mathematical kind of stimulus that I was getting besides chatting with Laurel because we lived together. So it was really a big relief to have this reading group trying to understand Vishik's papers. That was Camilo's idea. He said, people don't understand these papers. We're going to try to understand them. I guess this originated in discussions between Maria and Camilo beforehand. And anyway, so we had this reading group, and Camilo said we're going to write lecture notes. And and so we did, and they'll be published in they'll be appear in book form at some point. So, all right. Let me explain a little bit about this. So basically, if you want to prove this theorem, you again want to follow this. You want to follow this strategy 2. Find an unstable, self-similar solution, but you're allowed to have a force. So in other words, you just need to pick some unstable, self-similar object, and you call it a solution because the force is going to be the right-hand side. Again, it's what Gianluca Crippa introduced, which we talked about last time as well. So what's the scaling you're going to use? Okay, the scaling you're going to use is, it's actually going to work like this, okay? So you're going to take a steady state. You're going to take a steady state of 2D Euler. So in other words, I'm going to call it capital U bar. So capital U bar satisfies steady Euler. And in this case, it satisfies it without a force. It's a true steady state. It satisfies it. Satisfies the equations. And then we're going to define, just simply going to define a self-similar solution. Define a self-similar solution. U bar, little u bar of xt is t to the 1 over alpha minus 1, capital U bar, x over t to the 1 over alpha And you don't need the log t, just you make this definition. So, by the way, why this scaling? This is the scaling that you get when you identify length to the alpha with time. And when alpha, this scaling is basically compatible with omega naught in the weak LP space with p equals 2 over alpha. So as you send alpha to 0, you're increasing p and getting closer to bounded vorticities. And I put this weak LP space because the vorticities that you're considering, it's like they have power law decay, so they won't exactly belong to that endpoint LP space. They belong to the weak variant. Okay, so why do you have this? It's because t to the 1 over alpha is length, and then this minus 1 is 1 over time, so it's length over time because it's the velocity field. So this, when you just plug this in, okay, so you just plug this in, and this equals 0, just by unfolding. Okay, and so now the right-hand side, f bar, is simply the time derivative of u bar. So there's a force, it's the time derivative of u bar, because you're taking a steady state and you're just rescaling it because you can, and that generates a force, and this is the object that we're going to work with. So now what you do is you ask that, so you ask that this steady state is unstable. Okay, so I want to find an unstable steady state of 2D Euler. And, and then you hope that this u bar that you defined is going to be an unstable self-similar solution. So that is, you hope that in this procedure, the instability is kept. And there's actually a perturbative way. I mean, if you set everything right, set everything up correctly, then there's a way to think of this perturbatively, and it's actually true. So I'm not going to talk about that today. I'll explain that tomorrow. So basically tomorrow, I'll explain all spectral perturbation theory arguments. Today, I'm just going to explain how to construct this today. Okay? So you hope that little u bar is unstable, and that's tomorrow. Okay. Questions about this? Great. So now, okay, I said that this is what we're doing today. So all we need to do is construct an unstable steady state of 2D Euler. And 2D Euler has a large explicit family of steady states. So we're going to talk about shears and vortices. Shears and vortices. Okay, so what's a shear flow? This is a shear flow. For any shear profile B, this solves 2D Euler. So what you basically imagine that you're in a channel, and everywhere the flow just goes left or right, and the speed with which it goes left or right just depends on your height in the channel. So people typically draw it like this. So it suffices to draw what it looks like at a single x, and then they often just draw something like this. So or something like this, for example. So this is how people in the physics literature draw the shear profile. Now, what about vortices? Vortices, any radial vorticity satisfies 2D Euler. So then u is going to be only in the e theta direction. So u is some v, which depends only on r, and it goes in the e theta direction. So, I mean, if you have to visualize these, the streamlines are circles. I'm about to draw something I've never drawn before. It's easier not on the tablet. The streamlines are circles, and all right, you can also imagine there's like some profile here as well. The amount that you go in the direction of these streamlines. How do I want to do this? Usually it's something like this. The amount that you go in the direction of these streamlines depends only on the radius. So if you, in the end, we want to have finite energy solutions. So vortices seem like a good candidate because they're radial and you can make them decay at infinity, and even if they did just decay a little bit, if you cut them off, then you can make them have finite energy. So vortices are a good candidate. That's what VII used. So for his strategy. So there's just a theorem. Also VII, 2018. It's the part 2 of his two papers, and it's just there exists an unstable vortex omega bar. You can actually go a little farther. You can truncate the velocity of this vortex so that the velocity is compactly supported and keep the vortex unstable. So in fact, there exists an unstable vortex omega bar with corresponding velocity field compactly supported. And that's just an observation that we make in our paper. It's not so difficult, but that's a small tweak you can make. Yes.
Do you think it's possible to do the same thing for a shear flow, where you compactly chop it off so that it's not?
I think so. Yeah, this is a point I'll make next. The shear flow, technically, the shear flow case is a little easier. That's why we're going to do shear flows today. But basically, there's no hope to get finite energy solutions from somehow cutting shear flows. Because, I mean, the reason this vortex cutting stuff, so if you have a vortex which is just decaying a little bit, if the vorticity is decaying a little bit, if you chop it off at a large distance, that's a good approximation. But if you have a shear flow, then, I mean, it's constant in one direction, and you try to chop it, and that's like approximating the function 1 by a function which is compactly supported. And I don't know why Maria and I spent like maybe a couple months trying to do that. But, you know, it was a good first try.
Right, but so you don't modify the vortex in the center.
Right, it's just cutting. Yeah. So, I mean, vortices are localizable like that just because of the expression. I mean, this VR, suddenly you multiply it by 5R, it's still vortex. So, I mean, and if you read this paper of Peter Constantine, Vlad Vickel, and Junhyun Lah on the Gavrilov solutions, they have some general condition for what steady states are localizable. But anyways, vortices definitely are. Okay, so if you want finite energy, then you want to use the vortices. But shear flows are technically easier. So if you want the analogous theorem for shear flows, then the idea for this goes back to, so for shears, the idea for this goes back to the 30s. So again, that's u equals b of y, comma 0. And there was a German fluid dynamicist, Tolmin, who in the 30s basically had something like the perturbation argument that I'm going to sketch if I have time. But he had an idea for how instability could arise in these shear flows. And then, there is also a very important work from the Russian school. It's Fadeev, and it's like 70s. But it's written in the style of the Russian papers at the time. So this was just like something like a summary of the presentation he did in Kolmogorov's seminar, something like that. And it's not, it's not like a proof in the modern standards, say. So Jiwoo Lin at Georgia Tech in the United States, basically for his, it's around 2002. Basically in his PhD thesis, he gave a rigorous proof of constructing a large family of unstable shear flows. So if you just want an example of an unstable shear flow, you can just take sine mx, or sine my for large enough m, and it'll be unstable. But if you want to do the vortex case, then it's helpful to first, for the shear flows, have a very large family. It'd like improve your understanding. And then that proof works almost the same for the vortices. So, I mean, shear flows are like vortices. Shear flows, I mean, basically, x is like theta, and y is like r. So the shear flow case is like the vortex case. You know, okay, it's like translation invariance in x or translation invariance in theta. So the analysis is similar. Okay, if you're trying to do inviscid damping, then the analysis is different. But for this, it's similar. So, so we're going to do some basic calculations with shear flows, which go back to Rayleigh, and get some idea of how to construct these families of unstable shears. If you want to, I mean, you can read this paper of Jiwoo Lin. I mean, he has the proof in full detail. I'm just going to explain some version of it. In our VII lecture notes, we also have like some heuristics. There's a section called something like a formal calculation or a formal expansion or something, which also explains what's going on. Okay. So without further ado, let's consider a shear flow in a bounded. So I mean, we're just going to consider it in R cross, I don't know, 1, maybe like -1, 1 shear flow. And okay, so you take 2D Euler, Laplace psi equals omega, u equals grad perp psi, and you linearize. So linearize. And you'll get, now omega stands for the perturbation. So you'll get, you linearize around u bar equals b of y comma 0. So, I mean, the general linearization is just u bar dot grad omega plus u dot grad omega bar. So this equals 0. And by the way, you can already read off some basic stuff about the linearized operator from this, because this term here, this term is antisymmetric, because u bar is divergence free. So, so if you were to multiply by a test function, you can just move that gradient right past u bar. This term is antisymmetric. This term is actually compact. This term's compact because u is more regular than omega, because u is one derivative better than omega. And that gives you the compactness. So you can actually, just from this abstract stuff, you actually know a lot of spectral information about the linearized operator just from those two observations. So this is like spectrum of the linearized operator. So this antisymmetric part, its spectrum can only be in the imaginary axis. That's just a property of spectrum of antisymmetric operators, or skew adjoint if you put it in the right functional setup. And these compact perturbations, they cannot change the essential spectrum of an operator. So you add a compact perturbation, it doesn't change the essential spectrum. All it can do is basically add possibly, eigenvalues out here, something like this, okay? And in principle, these eigenvalues could be kind of collapsing. They could also be forming a sequence that collapses into the essential spectrum. The theory doesn't rule that out. But okay, you have essential spectrum and you have eigenvalues. We're trying to study these eigenvalues. So now let's actually use the fact that, let's use what u bar is. Now when you use what u bar is, here's the equation. So by dx omega, and then this is going to be minus b double prime dx psi. So if you calculate the curl, if you just calculate the curl of this, then you get minus b prime. All right, so now let's take Fourier transform in the x variable. We're linearizing around something that's translation invariant in x, so you expect you can take Fourier transform. So then the equation is dt omega hat plus b of y. I'm going to use m. M is my wave number variable. So now this is b of y, I m omega hat m, minus b double prime, I m psi hat m. So this is our equation. Let's give this linearized operator a name. This is minus Lm applied to omega hat m. So the spectrum, basically you take Fourier transform, you have all these invariant subspaces, so the spectrum consists of the union of the spectrum of all the Lm. So now I just want to study the spectral problem for Lm. So I study, I'm going to study lambda minus Lm applied to some function, anyways, I'm going to study this problem. F equals 0. So I'm calling f omega hat m. I'm going to call phi psi hat m. In a second, we're going to stop writing m's. All right, so I want to solve this spectral problem. So that's basically lambda plus b of y I m f minus b double prime I m phi equals 0. And now I have these I m factors everywhere, except for lambda. So I'm going to say that lambda is minus I m c. Now lambda is a complex number, c is also a complex number. So when you do this, and let me just also say that lambda is unstable when imaginary part of c is greater than 0. So lambda is an unstable eigenvalue, meaning it's in the right half plane, if and only if c is in the upper half plane. All right, so now what you have is b of y minus c times f minus b double prime phi equals 0. And the last thing you want to do is use the equation which recovers phi from f. So you're going to use that Laplacian of the stream function equals the vorticity. So in this case it's dy squared minus m squared phi equals f. So now you plug in, and you have, so you just take this, plug it into here, and you get, let me try to write it really nicely because we're going to look at it a lot. B of y minus c, dy squared minus m squared, phi minus b double prime, also a function of y, phi equals 0. And also phi at phi satisfies Dirichlet conditions. Okay. So this equation was derived by Rayleigh, and we call it Rayleigh's equation or Rayleigh's stability equation. That's the equation. It's the eigenvalue equation for the linearized operator, but it's written in terms of the stream function because when you rewrite it in terms of the stream function, it becomes local. Okay, now it's, from a certain perspective, it's just ODEs. But okay, it's not easy ODEs, but now it's a local equation for the stream function. So this is the equation that we want to study, and we want to study for which b can you find solutions to this equation with imaginary part of c greater than 0, because those will be unstable solutions. So let's just make a couple observations. So a few observations. Okay, so I already told you imaginary part of c greater than 0 is the same thing as lambda being unstable. Next observation is conjugation symmetry. Suppose you just conjugate the equation, okay? B is real, so nothing happens. You get C bar. M is real. Phi does not have to be real. Okay, B is real again. Phi doesn't have to be real. Okay. So in other words, if you have a solution, phi C, then you're going to have another solution phi bar C bar. And what that tells you is that to every unstable eigenvalue, you also have a corresponding stable eigenvalue. So phi C, phi bar C bar. So actually, the spectrum of this operator, we can say a little more, the spectrum of that vorticity operator, we can say a little more about. So we go back here. This is a multiplication operator. It's multiplication. And then this was compact. So again, the spectrum is like this. But to every unstable eigenvalue, there's also a stable one. And these have to be here simply because the operator, is real. So for every complex eigenvalue, you also have its conjugate. Okay, so this thing here, let me say that's what's going on here. Okay. Lastly, the equation is symmetric with respect to m goes to minus m. So without loss of generality, let's just say that m is strictly greater than 0. When m is equal to 0, it's kind of a trivial case. All right, so the way that people think about this, one way that people think about this equation is you want to divide through by this factor here. So let's go to the new page. Let's try that. All right, so let's say that you divide through by this factor here. All right. No. Okay. So this is your new equation. This is a steady Schrodinger equation with some kernel k. Something like that. Let me not name it yet. Okay, this is some potential. This is some potential k. Now, you would very much like to divide through and just study a steady Schrodinger equation because we know a lot about steady Schrodinger equations and the spectral problems for them. The problem is that you could potentially be dividing by 0. Okay, so when can you do this? So you can do this, one, if imaginary part of C is not equal to 0. So let's just focus on the unstable case, because remember, to every unstable eigenvalue, there's a corresponding stable one. That's the conjugation symmetry. Or you can do it if the numerator vanishes precisely when the denominator vanishes. So B prime vanishes where B minus C vanishes. And by the way, we're also, throughout, I'm going to assume that the shear is monotone. So the profile is increasing from bottom to top. Monotone. Yeah. So in that case, then, this makes sense. Okay. So, so we're going to, so we're very interested then in the place where B double prime vanishes. Okay, so B double prime, let's say B double prime at y0 equals 0. This is an inflection point. And it's actually known that inflection points are necessary to have instability. These are actually necessary for instability. That's Rayleigh's criterion. And oh, by the way, I mean all this stuff, okay, is like super classical. I mean, physicists worked out this stuff a long time ago. And if you just want to know more about it, then you can look at the book by Drazen and Reed. Reed. It's in the 80s. This is a book, and if you look at chapter 2 or chapter 3 in the book, then it's a whole chapter about shear flow instability. Okay. So that's another thing. By the way, if you work in this area, then you have to be at least I find, you have to be a little humble, because all these physicists did all this stuff, which is basically correct. And some of it's really at the level, and this is an exact calculation, it's basically at the level of mathematical proof. I mean, so, if one wants to enter the subject, then like, it's important to take seriously all the stuff that all these physicists did. Because if you just look at, let's say if you just look at the Vishik lecture notes and you just ask some question about it, you might find it's already known. You know, or if you just try to come up with some research question, you might find it's already been considered. So that's just an important point. All right, so it's necessary to have an inflection point to have instability. In fact, how do you show that? Is you multiply this equation by phi bar and integrate by parts. Okay, you multiply. So if we call this thing Rayleigh, so you actually multiply Rayleigh by phi bar and integrate by parts. All right, so here's the idea, which is already in Tolmin. So here's the idea, which is that unstable eigenvalues can bifurcate from neutral eigenvalues. So unstable evals, so in other words, imaginary part of C greater than 0 can bifurcate from neutral eigenvalues. What does neutral mean? Neutral means neither stable nor unstable. And in this context, it means imaginary part of C equals 0. So in other words, if you go back up here, this first case, solutions that satisfy this first case can bifurcate from solutions which satisfy this second case. But there's something kind of singular about this bifurcation, because this potential, when you move away from these points, when you move away from the inflection point, I mean, it's going to have some singularity. So, okay, so let's look at the inflection point. And I told you that we want B minus C to vanish at the inflection point. Okay, so B double prime y naught equals 0, and B of y naught equals, we define C naught, like this. So this thing actually has a name. It's called critical value. And this will ensure that our, if we impose this, this will ensure that our potential is well defined. So we go to the next page. And let me forget this m squared for a second. And actually, let me put it on the other side, m squared phi. Now this operator is going to make sense if here I put C naught. Remember, so this thing was equal to B of y naught. And so at the inflection value, this operator will make sense. And we can rewrite it like minus dy squared phi plus k naught phi equals minus m squared phi. So this thing here, without the minus sign, we call this thing k naught. That's our potential. Now k naught is approximately equal to, k naught is exactly equal to b double prime y over b of y minus c naught. And nearby, you have b double prime y. Then I can actually say this thing is approximately equal to b triple prime y naught over b prime y naught plus big O of y minus y naught, just by Taylor. And what you're going to use here is that from this, it's possible to design a shear profile B so that that potential is going to be really negative. Okay, this the way I've written it here, this is a positive operator. Okay, minus Laplace. I want this potential to be really negative, at least near a point, in order to generate a negative eigenvalue, and then this equation will be satisfied. So if you make k naught negative enough, so you can design B using this observation such that this thing plus k naught phi, such that this operator plus k naught, if you call this thing L naught, it has a negative eigenvalue. Which I'm going to call minus m naught squared. So you want to make k naught, so you want this to be negative, to be like negative enough. Okay. So then phi naught, and so let's call phi naught the corresponding eigenfunction. So in other words, L naught phi naught equals m naught, and then phi mc equals phi naught m naught c naught is going to be a solution of Rayleigh. This solves Rayleigh. And it gives you a neutral eigenvalue, or I'm just going to call it a neutral mode. So this gives you an object to bifurcate from. So therefore, there exists object to bifurcate from. So we're going to draw a picture. Picture is like this. Yeah, in fact, it actually needed a bunch of adjustments. Thanks, Sam. Okay, and in fact, phi naught. See, it still wasn't right. So we're going to draw this picture. I'm just going to draw here imaginary part of C. Remember, C is the twisted eigenvalue, and here is M. M is the wave number. So we could additionally put more axes, like an axis corresponding to the function space, an axis corresponding to real part of C. But what we have here is we have a solution, phi naught, M naught, C naught. That's the solution. And then the claim is that there's actually a curve of unstable modes bifurcating from it. And the picture looks a little bit like this. There's a further argument to show that this curve actually makes it all the way, I mean, depending how you set things up, this curve makes it all the way over here. This curve has to continue, depending on if you set things up correctly. And so, because for every unstable eigenvalue, there's also a corresponding stable eigenvalue, this picture is mirrored down below. So it's exactly mirrored. Now, the other thing is that this angle here is not 90 degrees. This curve doesn't smoothly go through this axis, because you can calculate this angle. And we're not going to do it. But you can calculate this angle, and you can find that this is not a smooth curve through this. So then there are two parts to this. You need to get a perturbation argument to start this curve. Now you have the object that you're going to perturb from. But oh yeah, because by the way, if I didn't mention already, this L naught is a self-adjoint operator. So the spectrum's real. It's going to have this negative eigenvalue. This gives you something to perturb off of. And if you're an applied mathematician, then you're just going to say, well, phi is equal to phi naught plus epsilon phi 1 plus epsilon squared phi 2 plus dot dot dot. And m is m naught plus epsilon m1 plus epsilon squared m2 plus dot dot dot. And then lastly, c, which is the eigenvalue parameter. Okay. And you're just gonna plug these in, okay? And calculating the relationship between these values here, m1 and c1, is the same thing as calculating this angle. And it's necessary to calculate it in order to make your perturbation argument work. So anyway, so you do this, and eventually you can find that C1 is equal to this crazy expression. But by the way, if you just set out, so if you take this and you just plug in and you set out to start computing, you will be able to come up with this answer. Let me just write it out. Anyways, this formal argument is in the Vishik notes that we wrote, and it's also going to be in the type lecture notes that I write for this. This is still in the denominator, by the way. Principal value. Okay. So you can calculate C1 exactly. And this plus minus also has to do with the fact that you're calculating these branches. So that's enough for today, I think. But in the afternoon, we'll well, let me summarize. What have we done? We have at least given a somewhat convincing argument for the existence of a family of shear profiles which are unstable. If you did a similar argument, though more technical, for vortices, you would be able to find vortices which are unstable. So this gives you explicit unstable steady states in 2D. You can take those you can take those and try to solve this 2D Vishik non-uniqueness problem. And if you do something in 3D, if you can get a 3D unstable steady state, then maybe you can do the 3D Navier-Stokes problem. That's what I'll explain in the afternoon. Okay, that's enough. Thanks.
We have quite some time, so are there questions, comments?
So just to make sure I understand the final construction, right? You have, you're trying to sort of globally continue this bifurcation back, but you want to go all the way down to m equals 0, or you just want to go to m as some integer?
Yeah, so the point Sam is bringing up is related. I'll answer the question in a second. The point Sam is bringing up is, let's say that you're studying this problem on the torus, okay? And you, now I've let my wave number m be arbitrary, but if you're on a fixed torus, then you really, like, let's say you're on a torus of like 2 pi, then you really want m to be an integer, and there was no guarantee that this number that I'm bifurcating from, m naught, is an integer. So you need to make sure that this curve actually passes through some integer values, so you can have instability on the torus. So there is a global continuation type argument for that. So the argument is roughly like this. You start this curve, and okay, you know that the curve will continue unless something happens. There are a few options for what could happen. One is that the curve could escape to infinity. So you rule that out. Another is that maybe the curve could escape to infinity this way, so you rule that out. I mean, for m large enough that you know there's no instability. The scary option is that the curve could fall back here. Now, what happens what you can show is that this curve can only fall at values where c is a critical value. So in other words, c needs to be b double prime of y critical, c needs to be b of y critical for some inflection point. And if you don't have any more of those, then the curve continues. On the other hand, if you do have more of those, then your perturbation argument, if you set it up correctly, will show that the only solutions nearby actually have to go this way. So in Lin's paper, he has so here's m naught, but okay, here's m1, here's m2. Okay, that ruins the perturbation notation. I mean, that ruins my asymptotic expansion notation, but those curves have to go to the left if you set it up correctly.
So you can have as many inflection points as you like, but sort of at each one you show that the bifurcation can only go one direction again.
Yeah. But in Vishik's, actually in the Vishik's thing, you can also have like m1, and the curve goes like this.
Oh.
Yeah. And in principle, you could have some picture that's stuff going like this, and I think Fadeev talks about that. He talks about some points are absorbing and some points are repelling. So, yeah.
Any more question, comment?
Yeah. You mentioned at some point that in the setting of shear flows there are really explicit examples of instability like
Sine
sine
y,
of.
yeah.
Do you know examples in the setting of vortices? Maybe they do not decay at infinity. So if I just put sine, it's not. I mean, if I just put something very oscillating without asking any decay at infinity, is there?
Yeah, for vortices, I don't know. Also, I think for shear flows, if you do like a step like this, you can show it's unstable. Ask Anuj. And you know, for vortices, people also study like a step vortex, but I think it's stable. It's ranking vortex. Yeah. So I don't know explicit unstable examples for vortices. That's the answer.
Thank you.
Yeah.
Any more questions? Okay, so if not, let's thank and Grain, and we resume to.
Okay, so we can start this afternoon session. The first speaker is Hyunju Kwon.
Yes, perfect pronunciation.
Okay, and she will speak about L3-based strong onsager conjecture.
Thank you for the introduction. Do I need? I have mic. Okay. Good afternoon, everyone. Also, first, I would like to thank to the organizers for having me here. So as you see from the title, today I'm going to talk about L3-based strong onsager conjecture on incompressible Euler equation. So on Monday, John Luca already explained what onsager theorem is. The outline of the talk will be first, I'm going to review what the onsager conjecture is, and then I will explain what I mean by L3-based and strong. And lastly, I will talk about the new developments in our proof. And this talk is based on my recent joint work with Matt Novak and Vikram Giri. Okay, so I guess now we are all familiar with this incompressible fluid equation. As you know, like when nu is positive, the equation is the Navier-Stokes equation, while when nu equal to 0, we call as the Euler equations. In this talk, the main focus will be the Euler equation, and we're going to restrict our attention to the spatially periodic domain. Okay, so if you assume the solution to this Euler equation is smooth, say it's differentiable in space-time, and then if you, inner product the momentum equation with velocity, then by simple computation you can easily get the following local energy equality. Although it's easy to obtain, but it has important physical meaning. So to see this, let's take the integral over the arbitrary local region on in a space. Then you will get the following equality. And from here, you can see that the kinetic energy on the omega, which is defined as the 1/2 of the square integral of the velocity over omega, and the rate of change of this quantity will be balanced with the flux through the boundary. So this means that there's no essential creation or dissipation of kinetic energy. In other words, the kinetic energy is conserved in the region omega. And since this omega is arbitrary, the physical meaning of local energy equality is that the kinetic energy is conserved in every local region. And in particular, if you take this omega as the whole spatial domain, we have total kinetic energy conservation. Okay, so although this total kinetic energy conservation is a special case of local energy equality, let's just focus on this total kinetic energy conservation. So onsager theorem was about the following question. Does the total kinetic energy conservation extends to irregular solution? And in fact, onsager proposed the conjecture in his explanation of the negative evidence, which is the anomalous dissipation observed in the turbulent flows. So this anomalous dissipation refers to the following. When you measure the mean dissipation rate of total kinetic energy of turbulent flow and send nu to 0, so viscosity to 0, then the rate does not converge to 0, rather it converges to some positive number. So unlike the smooth solution to the Euler equation have total kinetic energy conservation, if you consider the turbulent flow and at the vanishing viscosity limit, there are still remaining dissipation. So around 1940s, physicists tried to explain this anomalous dissipation. And onsager's explanation was the following. Such dissipation can originate from a potential singularity of solution, in other words, irregularity of the solution. So through the energy transfer from large scale to small scale, or small frequency to high frequency. So even without friction, so even in the Euler equation can have total kinetic energy dissipation. And onsager proposed even the critical space for the total kinetic energy conservation, which became the onsager's conjecture among mathematicians. But now we have a mathematical proof, so it is called the onsager theorem. So statement of the theorem is the following. If a weak solution to the Euler equation is in the following space, so onsager measures the regularity using Holder regularity. For alpha, the Holder exponent alpha greater than 1/3, then total kinetic energy is always conserved. While if alpha is less than 1/3, the conservation may fail. In other words, one can find a weak solution whose total kinetic energy is not conserved. So this rigidity part was already proved by Konstantin E. and Titi in 1993, building upon Eng's work. On the other hand, this flexibility part has a bit longer history. So in 1990s, Schaeffer and Schnirelmann first constructed the non-conservative weak solution. So these solutions are have just a L2 regularity in space. And afterward, Drellis and Cyclidi first adopt convex integration scheme to the fluid equation and constructed non-conservative bounded weak solution. And after several partial results, eventually ESET gave a full proof of the onsager's theorem. But the ESET solution has the creation of total kinetic energy in some time interval, which is not allowed in a physical world. So afterwards, Buckmaster, Drellis, Cyclidi, and Bicol constructed a solution which really dissipates the total kinetic energy. So this was the history behind the behind the onsager theorem. But I'd like to note that at the critical case, when alpha is equal to 1/3, the question whether the total kinetic energy is always conserved or not is an open question. Okay, so since we have this construction of solution, a natural follow-up question is the following. Are the constructed non-conservative solution physical? More precisely, are these solutions aligned with some of the physical phenomena or physical laws? In this talk, I'm gonna consider two physical features. One is intermittency of the turbulent flow, and the other one is the local dynamics of kinetic energy. Okay, so let's first talk about intermittency. So this is another feature commonly observed in the turbulence flow. And let's start with the scaling law. So when you consider this piece order structure function defined as follows. So here the bracket is the space-time average. So you first consider the velocity increment and then take the piece and raise the piece power and average it over space-time. Then it shows some persistent power law scaling when L is in the inertial range. So this scaling law suggests that the reasonable space for the turbulent flow would be the following Bezoff space, where the differentiability parameter is given as the exponent over P. Then our question would be, what should be this differentiability parameter as P? Interestingly, the original Kolmogorov's prediction was as P is equal to 1/3 for any P. And indeed, if this is the case, the Holder space C1/3 would be the right space for the turbulent flow. But in practice, the Kolmogorov's prediction seems to be only true when P equal to 3. So as you see, when you consider S3, numerically you can really confirm that it is equal to 1/3, but otherwise there has been the deviation has been observed. So more precisely, when you consider P less than 3, this differentiability parameter stay above 1/3, while P is greater than 3, this differentiability parameter stay below 1/3. And in particular, if you look at the paper of years in Nibazan Yang's paper, then as P is even converts to 0 as P goes to infinity. All right, so reflecting such intermittent nature of the turbulent flow, after the onsager theorem, this intermittent onsager theorem has been introduced. And this theorem was resolved by Matt Novak and Vlad Biko. So the statement of the theorem is following. They constructed a weak solution to the Euler equation in the following solution space, which exhibit total kinetic energy dissipation. So as you see, if you look at this solution space, you can see that when you measure the constructed solution in a different LP space, then you get the different differentiability. And in particular, if you measure in L3 space, the differentiability parameter stay close to the 1/3. And if you measure in L2 space, you really get the differentiability parameter greater than 1/3. So it sort of reflects the experiments on the intermittency. Okay, this is not the one. Okay, and I just want to note that their work was building upon their previous work together with the Buckmaster and Masmoudi. Okay, so this was one direction of research after onsager's theorem has been proved. And another direction of research is the following. So now we want to consider the local dynamics of the kinetic energy. Actually, this direction of research was even started before the onsager theorem was resolved. Okay, so recall that we know the smooth solution satisfies the local energy equality. And if you consider the anomalous dissipation of total kinetic energy, the kinetic energy, we expect probably some extra dissipation of kinetic energy is possible. But however, the creation of kinetic energy would be won't happen in the real world. So reflecting such observations, it is natural to expect the physical solution to the Euler equation to satisfy the local energy inequality. So here the equality really says that conservation holds, then inequality corresponds to the dissipation. Okay, so aside from this physical meaning, there are a few significance in this of this inequality. So first, it gives a direction of time. In fact, the Euler equation is time reversible, while Navier-Stokes equation is time irreversible. So for given solution to the Euler equation, if you try to approximate by solution to the Navier-Stokes equation in a vanishing viscosity, sometimes you have an issue because of this discrepancy. And but if you require the Euler solution to satisfy the local energy inequality, you can get around this issue. And another point is you can consider the Euler equation as the hyperbolic conservation laws. Then in such context, the local energy inequality corresponds to the entropy inequality. So entropy inequality in the hyperbolic conservation law were introduced to single out physical solution, and that works successfully for Burger's equation, for example. Although we now know this local energy inequality doesn't guarantee the uniqueness of the bounded weak solution to the Euler equation, but still it is meaningful as an entropy inequality. And the last point is, this is proved by Dujon and Robert. If a physically relevant solution to the Navier-Stokes equation strongly converges to U in L3 topology in the vanishing viscosity limit, then this limit solution should satisfy the local energy inequality. Just to be precise, here what I mean by physically relevant solution is suitable weak solution that Dallas introduced yesterday. Okay. So now reflecting this local dynamics of kinetic energy, one can consider this strong onsager conjecture. So while the original onsager conjecture was about the total kinetic energy, the strong onsager conjecture is about the local energy. So if you look at this conjecture, when alpha is greater than 1/3, any weak solutions satisfy the local energy inequality. So here I put the two type of solution space. If you follow the history or the suggestion of the onsagers, then you can consider the solution space as a Holder space. But on the other hand, if you reflect the intermittency of the turbulent flow, the Bezoff space would be more reasonable. But in both settings, Dujon and Robert proved that the rigidity statement holds. On the other hand, when alpha is less than 1/3, the question is whether one can construct a weak solution in the following space which satisfy the local energy inequality but not equality. So apparently, indeed it is easy to see that both rigidity statement and flexibility statements are stronger than the one in onsager's conjecture. I think rigidity statement easy to see. If you look at the flexibility statement, since the solution satisfies the local energy inequality, the kinetic energy will be either dissipates or conserved. But since the equality does not hold, there will be some reason that we have really the strict dissipation. So you can see that the total kinetic energy will be dissipated. All right, so for this flexibility statement, and if you just work on this Holder space setting, the current best partial result is the following. When you consider alpha less than 1/7, then we can construct the weak solution in the following Holder space, which satisfy the local energy inequality strictly. So this is my joint work with Direllis. And this work was building upon the ESET's work. Okay, but as we discussed, probably the Bezoff space setting could be more reasonable. And in this setting, actually you can fully resolve the strong onsager conjecture. So this is my recent joint work with Giri and Nova, and what we proved is the following. We constructed a weak solution to the Euler equation in the following region, following space, which satisfy the local energy inequality and total kinetic energy dissipation. So as in the onsager's theorem, the solution indeed have a total kinetic energy dissipation, but in addition to that, reflecting the intermittent nature of turbulence flow, the solution has this intermittency, and also considering the local dynamics of kinetic energy, the solution satisfies the local energy inequality. So, okay, but before we move on to the proof, I would like to share one observation. So this onsager type of theorems has been proved based on Nash's iteration, broadly referred to as a convex integration. And this Nash's iteration is a construction method which fully relying on the nonlinear structure, the nonlinear term in the equation. So if you look at the equation, there is a quadratic nonlinear term, while if you look at the local energy inequality, there is a cubic nonlinear term. So there is some structure difference between this nonlinear term. But if you work on the Holder space setting, you don't get any benefit from the structural difference, because you are working on LP space means that when you measure in different LP space, you actually get the same size essentially. But on the other hand, as you see from our work, if you move on to the Bezoff space, and especially working with this intermittent flow, you can get full advantage of this structural difference. And that's how we can reach near the critical number 1/3. Okay, then for the remaining time, let me explain the new developments in our proof. So for that, let me first explain how the conventional Nash's iteration works for the Euler equations. So Nash's iteration generates a sequence of approximate solution by successively adding a high-frequency perturbation to the initial approximate solution. And as their limit, we obtain the desired solution. So let's consider a simple problem. Let's try to construct a non-trivial continuous weak solution to the Euler equation. So this is the setup. Let's say the Q-step solution. So let's denote the Q-step solution by UQ and PQ. Then it solves the Euler-Reynolds system given as follows. And the stress error inside of the divergence is denoted as RQ. I think yesterday Franco gave a nice explanation about this motivation behind the Euler-Reynolds system. Okay, so here one assumption on this stress error is that it is negatively definite symmetric matrix. But more importantly, we want this error converges to 0 as Q goes to infinity. Okay, then our problem is reduced to the following. For given Q-step approximate solution, how to construct a new perturbation, which actually has high frequency, such that the new error has a relatively smaller size than the previous step error. So for this, let's first consider the equation of the perturbation. So here the Q bar denotes the perturbation in pressure, but this will just set it as 0. So it doesn't bother us much. And here the only information that we know about the perturbation is it has a relatively high frequency than the previous step solutions. So to use that, we first split this equation based on frequency. Then from the low frequency part, we see the previous step error, RQ. And also, we see the low frequency part of the nonlinear term. Although W itself has a high frequency, but since high frequency interaction can generate low frequency term, the nonlinear term contributes to the low frequency part. And all the remaining terms go into the high frequency part. Okay, so our aim is to make the new error much smaller than the previous step error. And for that, we really need to cancel out the previous step error. And the only term which can do such job is the low frequency part of the nonlinear term. So the outline of the proof is first you construct a perturbation which solves this low frequency part equation, and afterward you do you estimate the new error by inverting divergence in the high frequency part equation. Okay, and the reason that we can expect the new error to be small is that all the left-hand side terms has relatively high frequency. And if you invert the divergence, you will gain a factor, the reciprocal of the minimum frequency of this frequency of the left-hand side term. And since this frequency of the left-hand side term has the frequency, the same frequency with the perturbation, so if you choose perturbation whose frequency is sufficiently large, you can make a new error small. All right, and now let's see how the perturbation looks like. The answer of the perturbation is the following. So here we take the summation over some finite set of vector. And for each f, the perturbation consists of the low frequency part and high frequency part. The low frequency part will be determined in terms of the previous error RQ. And we have actually more freedom in high frequency part, especially the choice of the building block flow. But for the convenience, for now, let's consider the plane waves with the trigonometric function profile. So what you can think of this high frequency part is either cosine or sine function, which is rescaled by lambda q plus 1. So such function will have a frequency localized at lambda q plus 1. And for the different choice of vector f, we will assign a different propagation direction. And then if you plug such answers to the low frequency part equation, the low frequency part of the nonlinear term will reduce to the following using some assumption on the building block flow. And so the equation is eventually reduced to the following algebraic equation, and which is solvable by using Nash's geometric lemma. I guess that Franco will give more explanation about this convex integration scheme tomorrow. So for now, let me just summarize how this iteration works using the following picture. So assume that the previous step error has frequency localized at lambda q. And here lambda q, you can consider it as a double exponential function in q. And then we added perturbation w, which has frequency localized at lambda q plus 1. And we especially designed this perturbation to cancel out this previous error. Then all the remaining term will generate a new error, which has a frequency localized at lambda q plus 1. So from this picture, you can expect that the perturbation added at each step will have frequency separation, frequency support separation. Okay, and now let me introduce our new scheme, so-called wavelet-inspired Nash's iteration. So in the conventional scheme, as we just saw, the perturbations, there is a frequency gap between the consecutive perturbations. Just one side note is that unlike the previous picture, this WQ, the perturbation, doesn't have frequency localization at lambda q, Rather, it occupies wider range of frequency. This is because I included this. So this conventional scheme includes the one for the intermittent onsager theorem, which will be explained a bit more in a minute. But here my point is, even including such case, there is a frequency gap between the consecutive perturbations. So in this sense, the approximate solution, let's say UQ, which adds up all the perturbations up to WQ, can be considered as a wavelet partial sum of our limit solution. But on the other hand, in our new scheme, we consider the approximate solution as a wavelet partial sum. So as you see from this picture, we allow the frequency overlap between perturbations and resolve the issues arising from the overlap with the spatial support separation. So for this, when we construct a perturbation, we not only requires the frequency localization, but also we require spatial localization. And such information of localization is fully captured in the building block flow construction. So for the remaining time, let me try to focus on this construction of the building block flow, which is called the intermittent Mikado bundle. Okay, so let's go back to our perturbation. So the perturbation consists of the low frequency and high frequency. And in the previous discussion, we simply chose this building block flow in the high frequency part as a trigonometric function. Indeed, in the initial application of the Nash's iteration to the fluid equation, use the trigonometric function as the building block flow, well, more precisely Beltrami flows. But these flows are not very good building block flows for the wavelet inspired scheme, because this flow has a support which occupies everywhere in the domain. But there has been some development in this building block flow. So in 2017, Daneri and Saikahiri introduced the Mikado flows. The standard form of the Mikado flow has the following shape. So if you consider the easterly direction, this standard form consists of the given vector E3 and the associate function. And here, associate function is chosen to have E3 directional derivative is equal to 0. Then you can easily see that the function of such form solves the stationary Euler equation with 0 pressure. But more importantly, we're gonna choose this associate function to have support in a very small region in xy plane. So let's say its support is localized in the yellow circle. Then the associated, the standard Mikado flow will have support localized in this thin pipe. And then the general Mikado flow can be obtained by translating and rotating the standard one, and if it's necessary, by periodizing it on a torus. So apparently, unlike the trigonometric function, this Mikado flow has the spatial localization. And now when you consider the rescaled version of this Mikado flow, we can actually make it to have frequency essentially localized at lambda q plus 1. So, so for this, we're gonna additionally require the associate function to have mean 0. Then when you rescale it, the minimum frequency will be lambda q plus 1. But since this associate function is smooth, so it will have the rapid decay of the frequency. So in that sense, in the end, you can say that this rescaled Mikado flow has a frequency localization at lambda q plus 1. So, so therefore, this it is a good substitution of the trigonometric function. And using the benefit of this spatial support, it has been used as one of the key ingredients in the proof of the onsager's theorem. However, if you move on to the intermittent onsager's theorem, such rescaled Mikado flow is no longer good building block flow. The reason is the following. So it is because when you take the LP norm of this rescaled Mikado flow, their size are essentially same for different p. Then it's hard to expect that the velocity constructed from this rescaled Mikado flow have the different differentiability measured in different LP space. So to resolve this issue, one can consider the spatial localization of the base function. So here, the reason that we have the like no intermittency of this rescaled flow is the following. So if you consider the base function, the maximum of the base function and also this size of the support, both are of order 1. So when you consider their LP norm, their size are all of order 1. So instead, if you use their spatial localization, so this is the spatially localized version of the base function. Then, so first, to quantify this localization, we denote the thickness of this the pipe as RQ. Then the size of the support will be RQ square. And then to keep the L2 unit norm, that will the height of the peak will be accordingly changed to RQ inverse. Okay. And then you consider the LP norm of this new spatially localized base function. You indeed see the difference in LP norm size for different p. And okay, and for the rescaling parameter, we're gonna use the lambda q plus 1 RQ instead of simply lambda q, because we want the maximum frequency is lambda q plus 1. But because of this spatial localization, this base function already have the frequency, the derivative calls lambda q inverse. So to compensate that, the rescaling parameter is also changed. Okay, so now let's compare the original rescaled Mikado flow with this new rescaled Mikado flow. So original one, since it produced the same LP norm size, we call it as homogeneous Mikado flow, while this new one, let's call it as intermittent Mikado flow. So if you consider their support, since the rescaled Mikado flow, we rescaled this smooth function by the factor lambda q plus 1, the thickness of the pipe, and also the spacing between pipe, both are lambda q plus 1 inverse. On the other hand, if you consider the intermittent one, the thickness remains the same, but we have much larger spacing. But I think I forgot to say that this RQ will be chosen as some number small, between 0 and 1. Okay. Just 1 second. Yes, and okay, so I wanted to give one remark. So here in this intermittent Mikado flow, I just want to note that this thickness of the pipe corresponds to the reciprocal of the maximum frequency, and the spacing corresponds to the reciprocal of the minimum frequency. So as you see, from the previous picture, it actually occupies now wider range of the frequency. All right. Then, okay, so, and then you may wonder how this intermittency parameter has been chosen. So, since we want our eventual velocity to be almost bounded, we can't choose this intermittency parameter too small, because that will destroy the almost L infinity boundaries. On the other hand, we want this intermittency parameter as small as possible, so that we have larger spacing between pipes, and this will increase the chance of dodging the previously placed perturbations. Okay, then the question is, can we use this intermittent Mikado flow as the building block flow for the wavelet-inspired scheme? To answer this question, let me first specify our goal in the wavelet-inspired scheme. So as I mentioned, we allow the frequency overlap between perturbations. And in particular, the maximum frequency of the previous step velocity, uq, is much larger than the minimum frequency of the new perturbation. However, to have the desired regularity, as in the conventional scheme, we want the derivative cost of the previous step velocity is just lambda q, at least on the support of the new perturbation. So the trick is we construct a new perturbation to have a disjoint support with the all previous perturbations whose frequency is greater than lambda q. Okay, so now let me rephrase this question in terms of the building block flow. Then the question is, can we place a new intermittent Mikado flow to dodge previously placed intermittent Mikado flow whose maximum frequencies are strictly greater than lambda q? So these previously placed pipes will have thickness less than lambda q impulse. But the answer to this question is actually no, by some intuitive reason. So as we discussed, this intermittency parameter has been already fixed at the current step, and that fixed the spacing between pipes at the current step perturbation. And now, if the thickness of the previously placed pipe is smaller than this spacing, we at least have some chance to dodge this pipe. And indeed, it is the case. We can actually prove it using counting arguments employed in Matt and Blas' paper. The problem is there are still thicker pipes that we need to dodge, whose thickness is really greater than the current spacing. And for those pipes, the spatial support overlap is inevitable. So how should we deal with this issue? Our observation is the following. The periodicity does not necessarily detect the spacing between pipes. When you consider the intermittent Mikado flow, actually the spacing between pipes was determined by periodicity. But however, if you consider multi-scaled Mikado flow, this is no longer true. So here, this black term corresponds to the original intermittent Mikado flow. And I additionally inserted this blue term, which corresponds to the associate function to the homogeneous Mikado flow at the frequency lambda q plus epsilon. Here, lambda q plus epsilon is some number which is slightly larger than lambda q. And since its frequency is much smaller than the minimum frequency of the intermittent Mikado flow, it doesn't destroy the frequency localization. But the gain is, since this homogeneous Mikado flow has a support has a support contained in a pipe whose thickness and the spacing between pipes are very large. So through this multiplication, we can remove all the pipe outside of this support, and we gain the large empty rooms. And using this room, we can dodge the remaining thicker pipes. So this was the key idea in the Wavelet-inspired scheme. And because of this shape of the flow, we named it as intermittent Mikado bundle. Okay, so let me summarize my talk. So together with Giri and Novak, we resolved the L3-based strong onsager conjecture. And this conjecture really reflects the three features, three physical features. First, considering the anomalous dissipation, the solution actually dissipates total kinetic energy. And considering the intermittent nature of the turbulent, our solution is constructed in the following space, having different differentiability measured in different LP space. And in particular, when you measured in L3 base, we reach right below the critical number 1/3. And lastly, reflecting this local dynamics of kinetic energy, our solution satisfies the local energy inequality. And the new development is the Wavelet-inspired Nash scheme, where we allows the frequency overlap between perturbations and compensate it with the spatial support separation. And for this purpose, this results in the our new building block flow intermittent Mikado bundles. In fact, the proof involves with several additional features. First of all, inductively, we propagate point-wise estimate of the error and of velocity rather than LP norm estimate. And this is somewhat natural because we need to carry all the local informations. And there are also technical ingredients like intermittent pressure, which has some anticipating feature, and also a synthetic little Paley. But I guess, yeah, that's too technical, so I didn't include it. But if you want to know more, feel free to ask me. Okay, so let me stop here, and thank you very much for your attention.
So, other questions, comments?
Do you know of any convex integration situation, whether it be for Euler or isometric embeddings or whatever, which can really handle the endpoint case?
No. I'm not aware of it.
I've not fully understood. I would ask you to comment more how you do this game to spatially localize the objects, because you need a spatial localization, no? But you have to correct an error everywhere, so I don't really get, I mean, where the Mikados live, if they are like living holes. Yeah, I don't know if you can comment a bit more on this.
So the Mikado flows are in the end, leaves. So there will be this thick pipe, and inside of thick pipe, there's these thin pipes are living.
Yes.
So using this thicker pipe first, we dodge all this thick like perturbation which is added before, thicker pipe that we added before. And then using this, and then we choose this thinner pipe so that it dodges the remaining thinner pipes.
Okay.
But when you do the error cancellation, you anyway take integral.
So like the error is everywhere, no? I mean, at a certain step you have error everywhere. It's not that the error is localized. This is okay. But okay, so it's different from how I think it was.
Yeah, but when you match with error, you anyway take integral. So you just determine as before. It's a same.
I see. I'll ask you more.
Yeah, yes.
So, are there other questions, comments? Okay. So if we don't have other questions, we thank again our speaker. And I propose we just go on, since we are all here. And okay. So.
Sure, yeah, because there's more room, because you're only going up to.
Exactly. So they could. But even like just simpler like Arnold equation. So it would be nice to have one situation. We do a break or
Proposal by Daniele was to go on
go on?
and to make a longer break, but I
Yes.
we follow the host. Okay, so I think we have two tightly connected lectures now. The first of which is by Hyunju Kumar, Non-Uniqueness of Solutions of ODEs and PDEs with Sobolev vector fields.
Yes, thank you for the introduction and thanks for the kind invitation to the Riemann Prize Week. So today I'll be talking about non-uniqueness of solutions of ODEs and PDEs, in particular transport equation and continuity equation, where the vector field belongs to Sobolev space. So here are the transport equation and the continuity equation. And if you want to solve these two equations, then it is also very useful to consider this ODE, dx by dt equal to u, which is really the Lagrangian point of view. It is because if you could solve this ODE, then you can construct the solution of the transport equation and continuity equation using the method of characteristics or using a push-forward formula. And in this presentation, I will be considering a velocity field that belongs to Sobolev space W1P. And in most of the results that I'm going to present, the velocity field would be divergence-free. So before going to present the results, I want to say a few words about why we are interested in studying these equations and why consider velocity fields that are less regular. So transport equations and continuity equation often occur if you want to study fluid flows, but these equations occur in a coupled system of equations. So basically these equations are coupled with a governing equation for the velocity field. And in real life, you not only have transport phenomena, you also have other effects such as diffusion. So by turning off all the other effects, by considering only these two equations, it gives us an opportunity to gain a deeper understanding of, for example, transport phenomenon, and which can be potentially very useful when you go back to study the full coupled system of equations. And I should also say that velocity fields that are less regular also occur in real life. For example, if you want to study supersonic flows where you have shocks, the velocity is not even continuous. So that's another reason you would want to study velocity fields that are less regular. And the velocity fields that belongs to Sobolev space or of bounded variation, then there are theories where you can extend the notion of solution in a very natural way. So for Sobolev space, you have de Bernard-Lyons theory, and then for vector fields with bounded variation, you have theory by Ambrosio in 2004. Okay, so Now I will give a little bit of background and then I will show you the results. So in the first part of the presentation, I will be interested in studying this ODE, dx by dt equal to u. And for this ODE, if the velocity field is Lipschitz, then everything is known. Basically, that for every starting point, x0, there is a unique trajectory that exists. And by bundling these trajectories together, you have a unique flow map. So everything is known when velocity field is Lipschitz. But the velocity fields that I will be interested in would be where u belongs to Sobolev space W1P. And this is the basically this is the velocity field that falls under this realm of Depernat-Lyons theory. Okay. Yes. So some very basic definition. What is a trajectory? Trajectory is basically starting from a point x is a curve that solves the ODE and satisfies the initial condition. And a flow map is basically when for every starting point x, you take out a trajectory and you put them together, and then you bundle them together and you get a flow map. Okay. Now, for the purpose of this presentation, I will divide my flow map into two categories. This division is based on the definition from paper by Professor Ambrosio. And so the first classification is of flow map is what I call as regular Lagrangian flow. And it is that a flow map would be regular Lagrangian if for every set B that initially had positive volume, and if you let this set evolve under this flow map X, the volume stays positive, then this flow map would be regular Lagrangian flow. But the other category, which I would call as non-regular Lagrangian flow, would be that if there is a set B which initially had positive volume, but if you let it evolve under this flow map X, then it get crushed to a volume 0. So that would be non-regular Lagrangian flow, which is a not so nice category. Okay. Now, if the velocity field u is Lipschitz, then we know we have existence and uniqueness in this broader class of flow map. Okay, and so we have only one flow map, and this flow map happens to be the regular Lagrangian one. So for u Lipschitz, this category doesn't even exist. Okay. Now, for velocity field that belongs to Sobolev space and have bounded divergence, then there's a theory of Depernat-Lyons which says that that you have existence and uniqueness in this more restricted class of flow maps. So they showed that there is only one regular Lagrangian flow map. So after the theory, a question that remained open was that do you also have existence and uniqueness in this do you also have uniqueness in this broader class of flow map? Could it be the case that just like the classical theory, that you only have one flow map and it happens to be the nice one, the regular Lagrangian one? Basically, maybe even for this case, the non-regular Lagrangian flow category doesn't exist. So basically, that's the question that remained. And in particular, there was a question by Alberti who asked the following, that are there continuous Sobolev vector field for which non-regular Lagrangian flow exists? And the word continuous here is important because if the velocity field is continuous, then you fall under the Peano existence theorem. Okay. I will make a simple remark that if you want to prove the existence of non-regular Lagrangian flow, it is the same as proving that there is a set of positive measure of initial condition for which you have non-unique trajectories, because for this set, then there is two ways of picking trajectories, and you can bundle them together in at least two ways. And then there can only be one regular Lagrangian flow, so the other one has to be the non-regular Lagrangian one. Okay. So the first result that I refer to is by Pfefferman, Pulli, and Rodrigo, who proved that, who constructed velocity field that is LQ in time, W1 in space, and uniformly continuous. And they showed that there is a set of full Hausdorff dimensions, but of measure 0, such that the trajectories are not unique. So their result doesn't really prove the existence of non-regular Lagrangian flow because they are proving non-uniqueness only on a set of measure 0. And I should also say that I've not mentioned on the slide, they actually do not cover the whole range of exponent p. So it doesn't go all the way to infinity, it stops after finite p. Yes. So more recently, there was a result by Brouet, Colombo, and Delalis who constructed a velocity field that is continuous in time, Sobolev in space. They used the method of convex integration. They first proved non-uniqueness for positive solutions of continuity equation. And then using the Ambrosio superposition principle, they showed that, okay, the set of initial condition for which the trajectories are not unique is of positive measure. So basically, they showed, okay, the non-regular Lagrangian flow do exist in the de Bernalien's theory. And the range of exponent is a p that is strictly less than the dimension d. Okay. Then for exponent p larger than d, there was a result by Karavan and Kripa who showed that, okay, if the velocity field is continuous in time, Sobolev in space, then you only have one flow map. So basically, just like the classical theory, if the exponent p is larger than d, then you do not have these non-regular Lagrangian flow. So in that sense, the result of Brouet, Colombo, and Delalis is sharp. So you cannot go beyond p. Okay, so now I will discuss a few results that I've been working on for past few months. So the first result is that for any exponent p between 1 and infinity and Holder exponent beta between 0 and 1, I construct a velocity field that is divergence free. It is autonomous, and the velocity field belongs to W1p, C beta, such that there is a set of initial conditions of full Hausdorff dimension such that the trajectories are not unique. So this result is very similar to the result of Pfefferman, Pulley, and Rodrigo. The difference is that I cover the range of exponent that goes all the way to infinity, and also it has some Holder continuity. Okay. I will just say a few main ideas how to construct such a vector field. And the construction is actually based on simple example of 1D ODE, which is dz by dt equal to z to the power alpha. Now, for this ODE, we do have non-uniqueness on a set of positive measure. But this example doesn't really qualify in the de Bernalien's theory because the divergence is not bounded. But you could mimic this example in higher dimensions by going in higher dimension and making your velocity field divergence free, and that's basically what I will do. So the velocity field that I first give a 2D construction and then I'll go to 3D construction. So the example that I construct looks something like this. So this is the example of velocity field, and what I've shown here is velocity field at different section in z. So z equal to -1, z equal to -half, z equal to -4, and going up to z equal to 0. And the way I've drawn the velocity field is basically a physicist way of drawing, which Dallas already mentioned in the morning. So at every section, I have first a black line, and then I use arrows to show the magnitude of the z component of the velocity field, and then I put another line. So in this velocity field, what happens is that when you go from z equal to -1 to z equal to -half, the flow from some of the flow from the top and some of the flow from the bottom moves in the middle. So in the middle, the velocity increases, and on the top and on the bottom, the velocity decreases. So that's what happens. Okay, and the place where the velocity had increased, now I will not touch it. I will keep it untouched. But the places where the velocity decreased, I repeat the similar process. Basically, I take out sum of my flow and put it in the middle, and on the top and the bottom, the velocity decreases. And the velocity keep on decreases in a fashion z to power alpha, okay, such that when the particles that hit z equal to 0, then they can either decide to stop for some time or move immediately. So you have non-uniqueness at z equal to 0. So basically this example mimics the 1D example. But for this example in 2D, what can be shown that the non-uniqueness happens on a set of Hausser dimension that is strictly less than 2, so anything less than 2. But I was not able to make it exactly equal to 2. But there were some topological obstructions in 2D, which I was able to overcome by going into 3 dimensions. So basically, I do the similar type of construction in 3D, which mimics this 1D example. But in this 3D construction, so what I've shown here is the UZ component of the vector field for different slices in z equal to -1, z equal to -12. And the color shows the strength of the velocity. And I'm doing the same thing, that in the middle the velocity increases, and on the side velocity decreases, and then the process repeats. But in this 3D example, I was able to include a slightly different mechanism by going from z equal to -1 to z equal to -12, for using which I was able to show that the set for which the trajectories that are not unique is of full Hausser dimension. So it's dimension d exactly like dimension is d equal to 3. So this example, in a sense, shows that the result of Caravan and Kripa is sharp. That okay, you do not have non-uniqueness on a set of positive measure, but still the dimension can be very large. Okay, so this is the first result that I want to talk about. The second result that I have is, okay, what happens when the exponent p is less than d? So the result I just talked about was for any p between 1 and infinity, and so now I want to talk about what happens when p is less than d. So for p less than d, I construct a velocity field which belongs to space continuous in time w1p in space, and it also has Holder continuity of any exponent less than alpha, for which I show that the set of initial condition for which trajectories are not unique is of full measure. Basically this example then settles the question of Alberti, which basically says that non-regular Lagrangian flow do exist for continuous Sobolev vector fields. Okay, and this is a time-dependent example, but you could make it autonomous by going into higher dimension, d larger than 3. Basically, you trade time for one space dimension. Okay. So now I explained what are the main ideas involved in this construction. So I will be constructing a velocity field, U, that is Sobolev, and a corresponding flow map, X, which takes the whole domain and it maps it to a Cantor set such that the dimension of this Cantor set is strictly less than d. So the measure of this Cantor set is 0. So the flow map constructed in such a way would be non-regular Lagrangian because it's taking the whole domain and to a set of measure 0. Okay. And this basically shows, this figure shows the Cantor set construction process. Okay. Yeah, so the main idea goes something like this. Suppose you have a point in your domain, X. Now for this point X, there is a sequence. And what is that sequence? So you divide your domain into 4 cubes, and you look where this point lies. So this point lies on right and top. So I put 1 and 1, 1 for right, 1 for top. Then I further divide this first generation cube into the next generation cubes, and I see, okay, where this point lies. This time it lies -1 left top, so I put -1 and 1, and I keep doing that. Okay, so I have a sequence basically. So this is nothing but a binary representation. Okay, but now for this sequence, there is a point in the Cantor set. Basically, I obtain that point in a very similar way. Okay, I first select the right top cube in the counter set construction process, and then I select the left top cube in the counter set construction process, and I keep doing that, I obtain a point. So the velocity field that I would be constructing and the trajectory that I'll be building would take this point x into the this corresponding point in the counter set. Okay, so that's what I'll be doing. But so instead of showing you the velocity field that takes the whole domain to a counter set, I will do the opposite. I will show you a velocity field that takes the counter set to this full domain, and then I will just simply use a time reversal argument. Okay, so how do I do that? So this velocity field takes this counter set to the full domain in infinite steps, but finite time. So what this velocity field V does at every step, it takes the ith cube in the counter set construction process, and it moves it to the center of ith generation cube, dyadic cube. So that's what it keeps doing, this velocity. And after finite time, if I keep doing that, then after finite time, I'll take the whole domain. I'll take the counter set to the whole domain. Okay, and to move the cubes, I use what is something called as blow-up flow. So suppose you want to take this cube there. So what you do is that you construct a velocity field that is divergence free, and it's uniform where the support of this cube lies. And imagine that this velocity field is translating up and right in time, such that this cube only sees the uniform flow. So basically what happens then is that cube just gets translated. Okay, so that's how I move my cube. And just one remark that why I was able to control the Sobolev norm is because the size of cube in this counter set construction process becomes smaller, much smaller than the size of similar generation dyadic cubes. Okay, and it is easier to move cubes when you want to measure the cost in the Sobolev norm. Okay, so it's easier to move the smaller size cubes basically, and that's the reason I was able to control the Sobolev norm. So yes, that completes the second result. Now I will briefly talk about third result, which is a joint work with Alia Brue and Maria Colombo. So right now I talked about non-uniqueness of solution of ODE. What about non-uniqueness of solution of the continuity equation? In particular, we are interested in constructing Sobolev vector field and showing that there is a non-uniqueness in class of LP solutions. But in this presentation, I will just consider the L1 case when the density belongs to L1, class L1. Yes. So the construction that I had shown you, this already produces non-uniqueness in class of measures. But this example is actually nowhere L1 in time. So the goal was to produce non-uniqueness in class of L1. And this is what we were able to show, that in dimension d greater than 2 and any exponent p between 1 and dimension d, and you can also get a little bit of Holder continuity. There is a velocity field that is continuous in time, w1p in space, and then you have Holder continuity in space-time. And what we were able to show, okay, you have non-uniqueness in an L1 class. And the way we did that is we constructed a velocity field which takes uniform density, such that there is a solution which takes uniform density, and it concentrates the density on cubes of smaller sizes, and the magnitude of the magnitude of the density rises such that you have mass conservation. You have mass conservation in both the pictures. So the integration of rho is the same. Yes. Yeah, so because you also have a trivial solution, which is basically stays uniform, then you therefore have non-uniqueness. Okay, this construction, the construction for velocity field and density field will also involve a counter set this time in the time variable as well. So consider a time series that goes from tau 1 to tau infinity, something like this. So you have many intervals, tau 1 to tau 2, tau 2 to tau 3, and so on. Okay. What you do then in the first step, you divide these intervals, tau 1 to tau 2, tau 2 to tau 3, in half, and you only consider the right half. Okay. So that's what you take. That's what you're left with. And then you are also left with some blank intervals. And then in these blank intervals, what you do is you also take out some more part. So the way you take out more part is in the same fashion, in same geometric fashion, but you have inverted the geometric series, okay? You have just inverted that. And then you keep doing that, then you are left with a Cantor set of measure 0. So the density field that we would, the velocity field that we would be constructing and the density field we would be constructing, the density field, the L1 norm of the density field would be bounded almost everywhere in time except on this Cantor set where it will be represented only as a measure. Yes. So now I show you the significance of this Cantor set. So as I said, I will be constructing a velocity field for which there is a solution that takes uniform density and concentrates into smaller 4 cubes. But I instead will describe the velocity field that does the opposite, and then I can use the time reversal argument. So the way I do it is basically you start with 4 cubes where the density concentrates, and you somehow these cubes break into 16 cubes, and I'll explain how in a second, but somehow you assume that these breaks into 16. And then what you do in the first blue interval, you spread them. You spread them using the blob flow that I described it to you. So on this first blue interval, you have the explicit definition of velocity field. Okay. And then in next blank, white blank interval, what happens is that somehow the cube breaks into 64 cubes, and I'll explain how. But in the second blue interval, then they spread in the same fashion, and you keep doing that. Then you will converge to uniform density basically weakly. Okay, so I will show you what happens. I will tell you the construction in this blank interval. How do I do that? Okay. So as I said, these 4 cubes will be breaking into 16, and in the blue intervals, I'll be simply moving them. So in this first white blank interval, we notice that this cube breaks into 4, okay? I mean, total 4 into 16, but this cube breaks into 4. But this is nothing but the smaller version of original problem. That's what it is. So basically, then this motivates defining the density field, the velocity field and density field in an iterative manner that you can keep doing that. So this motivates setting up a fixed point argument for the velocity field, for example. So here I define a relation v equal to fv, where this functional fv has explicit definition on the blue intervals, okay? And on the blank intervals, it is a rescaled copy of itself, okay? Some rescaled copy. Then what we show is that this f here is a contraction in this following space. So basically, there's a fixed point to this relation, and we have a fixed point to this relation, which lies in continuous in time, Sobolev in space, and some Holder continuity. Okay, and then one can do same thing for the density field. Okay, I defined a relation rho equals g rho, and g rho has some explicit definition of the density, and then some self-similar copies. And then you show, okay, even this g is a contraction in appropriate space, which is Ls in time, L1 in space, and Lipschitz in time, and W minus 1Q. And actually, I mean, here the exponent in time is Ls as less than infinity, but I can make it L infinity. Once we find the object, then you can upgrade it to L infinity. And it's not very difficult to show that the solution found in such a way to these relations, these two relations, it actually solves the continuity equation. This you can do using, again, a very simple iteration argument, which is that On the blue intervals, you have explicit definition. So you know that the density solves the continuity equation on those blue intervals. But then using these fixed point arguments, you can basically upgrade it to, okay, the density solves the continuity equation almost everywhere in time. But because you have this Lipschitz continuity in time, you basically know that it solves the continuity equation in weak sense. Yes, so this is all I had to say about the L1 solution. Thank you.
So we have time for some questions, even in the middle of the two talks.
I was wondering if you could say a little bit more about what the topological obstructions are in 2D versus 3D.
Oh, yes, yes.
Thanks.
Yes. So in this construction, some of the particles will eventually come to an halt at z equal to 0, right? And this, if I only look at this section z equal to 0, and I look at the particles that come to halt only at z equal to 0, I can actually make this set of whose one-dimensional measure is positive. I can do that. But if I look at the pre-image where they came from, the Hausdorff dimension of those, if I consider any other section, would be less than 1. So it's like 1 cross something that is less than 1. You get something less than, and it has it has everything to do with incompressibility condition, which is very simple. That if you're stopping something, if this line is going from here to here, and you have incompressible velocity field, and the velocity field here is smaller, and if you go backward, the length of this thing shrinks. So I can have something that has full Hausdorff dimension here, 1 dimension here, but if I take its pre-image and at any other section, its Hausdorff dimension will be strictly less than 1. So that's the region. But I was able to overcome in 3 dimensions, basically. Yeah.
Are there other questions or comments?
Have you tried to see, in the paper of Pfefferman, they have various results, also now certain measures are deformed, and so have you tried to get like their results or better, perhaps, with your method?
So actually, there's a reason why why one cannot obtain non-uniqueness on a set of positive measure using their construction. There is a fundamental restriction, and which is that for them the non-uniqueness happens at the origin in their coordinate system. Okay, so the set that they have moves to the origin. Okay, and then it can choose to move anywhere. Okay, so if you have non-uniqueness that happens because of the choice of the direction, it cannot work, because suppose it were to work, let's say it were to work. So there is a set of positive measures that is moving towards the origin. Okay, then I can either let this set leave in this direction or that direction. So that would mean that there could be 2 regular Lagrangian flow, which cannot happen. So that's the fundamental restriction. That's why their example cannot work. Yeah.
Okay. One final question or remarks? Okay. So we can thank again our speaker. So we go on. Our next speaker is Bill Coopermam, and he will talk about exponential mixing by shear flows.
Is this okay? Thank you. Thanks very much for the invitation. It's great to be here. Yeah, so I'll get right into it. I was just going to talk about exponential mixing by shear flows, but maybe this is a bit of a misnomer, because sort of maybe half the talk will just be general sort of facts about mixing, and then part of it will be focused on shear flows. So the setup is we want to do all of our work just on the flat torus in 2 dimensions, just for simplicity. I think all of the results I'll mention work in general dimension. Maybe there's issues with the boundary, so it's nicer to work without boundary on the torus. But the d equals 2 is just sort of for convenience. And if I have a subset of the torus, I say that it's mixed to scale epsilon if whenever I draw a ball of radius at least epsilon, at least a third of that set intersects the ball, and at least at most 2/3. So it's sort of it's telling you sort of if you have a plate and half of your plate is ketchup and the other half is mustard, and you mix it up and you look at a small piece of radius r, then it should be close to orange, not too red, not too yellow. So if you have any sort of divergence-free vector field, as we've sort of talked about already a lot, you can consider the associated flow maps. So I just solved the ODE following the velocity. And I should mention maybe like for this whole talk, you can assume B is smooth just qualitatively, because my main focus is just on the estimates. So if you have an estimate for smooth B, then by approximation you can get it maybe for B in some Sobolev space. But I'm just concerned with the inequalities. And the motivating question is if we have some control over B, maybe in some Sobolev space, then how well mixed can we make some set after flowing for a certain amount of time? So if I have some set E, which maybe is a ball or maybe is a rectangle or something like that, then I can ask how mixed up E can be after I flow for time 1. And I should mention sort of, if anything's unclear, please stop me, interrupt me, feel free. So I guess I want to start with some pictures of mixing, which maybe won't be new to the audience here, but I think they're nice to look at. So this first one, it's a little bit hard to see because we're taking pretty large time steps in between So we're taking pretty large time steps in between the snapshots. But the vector field here is sort of the alternation of 2 different vector fields. So the first one is sort of a sine wave where it's vertical. The profile is a vertical sine wave. And the second one is a horizontal sine wave. And I just alternate them, and at each step I pick a random phase. So this is something that Sam talked about yesterday. And so the nice thing about this vector field, at least from the mixing perspective, is it's very regular. I have bounds in all the CK norms. And yet you still, from numerical experiments, you expect exponential mixing. And this was something that was conjectured by Pierre Imbert back in the 90s or 80s, I think. But it was recently proven last year by Alex Blumenthal, Michele Cottisolati, and Rishabh Gulani, where sort of they have this general random dynamical systems framework where sort of they actually prove exponential mixing for a pretty broad class of random flows. And sort of whenever you have enough freedom in enough randomness, and as long as you don't have silly problems like periodicity, you're going to get sort of exponential mixing just using their method. So this is one picture. This is another picture where instead of taking alternating sine waves with random phases, we take alternating sine waves with random durations. So in the previous picture, we run each sine wave for, say, 10 seconds and repeat. In this one, you run it for some random amount of time, and then you run the next one for an independent random amount of time, and you keep going in this way. So this still mixes exponentially, but it's actually, it doesn't quite fall into their framework because there are a few fixed points of this flow. So if you look at the zeros, or I guess I can draw here. So there's a 0 here, and then at each of these corners of the flow, and those points never move. So it's a little bit trickier, but it's not much worse, because if you really zoom in at what's happening at the zeros, or the fixed points of the flow, there's a strong shear. And sort of as was already discussed in the past few days by several good talks, this shearing is really what's responsible for the mixing. And so the fact that you're a fixed point isn't really a big problem as long as you have a strong shear. So this is sort of a non-example of mixing, because I still have the situation where the 4 fixed points that I pointed out earlier are experiencing a shear. But if you run the flow for exactly time 1, so I'm choosing things so that the sine wave has magnitude 1. So in time 1, the sine wave at the peak, it wraps around exactly once. So if you do this, then you get these islands here that get mapped to themselves. And now these are fixed points, but they're fixed points where the derivative of the flow is also 0. So if you sort of zoom in, the size of these islands is only decaying polynomially, or like 1 over polynomial. So you can't hope for exponential mixing. I don't know if I'll be able to click this. So this is another, does this work? Oh, OK. So this is another example of failure of exponential mixing. And in this case, what we're doing is we still have random durations, so that's not the problem. You don't have to worry about fixed points, but we're doing this sort of discrete shear where there's a jump. And so if you imagine that you're a little ball of radius epsilon that's walking around in this picture, you expect that it's going to take time 1 over your area, or 1 over your side length, until you run into this shear. So you just have to, the typical ball has to wait far too long until it hits the jump. Let me see if this still works. That might have been a risk. OK. So that's the end of the pictures. So there is some other motivation, which is Alberto Bressan's mixing conjecture. So this picture is, I should mention, this picture is from his paper on his website, where he proposes the problem. And so what Bressan conjectured was that if you just have control over the L1 norm of the gradient of your vector field, and I'm only taking the gradient in space and not in time, which is kind of important, then you shouldn't be able to do better than exponential mixing. So any vector field that is the gradient is controlled in in L1 can't mix faster than exponentially. And he offers $500 for anyone who solves it. Although there's an asterisk, which I'll explain in a moment. So, let's see. So why is this a reasonable conjecture to make? Well, I guess the first basic fact is just if you replace the L1 with L infinity, then this is easy. So you can find, if you have a vector field that mixes down to scale epsilon, then you can find 2 points that start far apart, some macroscopic distance apart, and at time 1, they end up within epsilon distance. And all I have to do is sort of pick any 2 points, so pick any 1 point from sort of the center of A, see where it gets mapped to, and then pick any point from A prime that gets mapped nearby, and those are going to satisfy it. And so sort of by just fundamental theorem of calculus and Gronwall's inequality, if you have 2 points and you have a Lipschitz vector field, you can't separate faster than exponentially. So there's an upgraded version of this L infinity result, which is by Gianluca Crippa and Camilla Delellis in 2008. So a year or two after Brisson proposed the conjecture, and they solved it for all p greater than 1. So the only remaining case is p equals 1, and this is why there's an asterisk here, because maybe if you solve the p equals 1 case, maybe they deserve $499 of the 500. But still, the p equals 1 case is remaining. So I thought sort of my plan was, since a lot of these mixing results have sort of very short, very elementary proofs, I thought I would try to at least give a sketch of most of the recent results, and then try to compare and contrast the different proof strategies. Because it seems like so far there's really only one main strategy that has worked. And it's the same one that's here, actually. So how does their proof go? OK, this is a slightly different proof than the one they gave, but it's basically the same. So if you have your two sets, A and A prime, so remember A and A prime are the left and right half of the torus, then you can consider the cost of optimal transport from sort of Lebesgue measure restricted to A to Lebesgue measure restricted to A prime. But the trick is that you let your cost be the log of the distance that you travel. So it's really important that you let your cost be the log, because this allows sort of points to locally tell what scale they're mixed to. So for example, if you try to just take the quadratic cost, then you'll see pretty soon that this approach isn't going to work. So this functional, as far as I know, this was, I first saw this in a paper by Christian Sayce in 2017, where he was using this to prove stability estimates for continuity equations. So it's pretty similar. And so the main observation is that I think of this optimal transport cost as an energy. And you observe that the energy at time 0 and the energy at time 1 are very different. So if you're very far apart, like on the left, then your optimal transport cost is going to look like, well, your typical path is going to be of constant order. And so since I'm dividing by epsilon, your optimal transport cost is going to look like log epsilon. And on the right, everything's pretty close to each other. So actually, if you're not perfectly mixed, it might not, the optimal transport cost might not be on the order of constant, but at least the coefficient of the log epsilon is getting smaller. So there actually is a difference. So there's a difference between the initial energy and the final energy that's of order log epsilon. And so this is actually exactly mirroring the case when p equals infinity, because here our energy is just the difference between our two special points. And it starts out, if you take the log, then it starts out at constant and ends up at epsilon. So if you want to complete the proof, then exactly as we did before, we have to show that if the energy starts somewhere and ends up very far away, we have to show that the rate of change is controlled by the derivative of our vector field. And so this is sort of where the trick that I first saw in Crippa and Delellis' paper is really used. And so the idea is that when you take the derivative of the log, okay, you get some difference quotient for your velocity field. And then you can actually pointwise bound the difference quotient for the velocity field by the maximal function of its gradient. And so this is like sort of like it was new to me, but I guess this is some sort of standard maximal function estimate where sort of to go from x to y, you first go from x to the average in a large ball centered at x, and then you go from that ball to y. So it's sort of the same trick that you always see with maximal functions. And then once we have this, we just integrate up in x and y and use the fact that the maximal function is controlled by the gradient since we have p equals 1. So this is, you know, almost all the way there. The only problem is that the constant depends on p and it blows up as p goes to 1. So what's known about the endpoint case, p equals 1? Well, as far as I know, there's no known rate. So forget about like exponential. You can stack as many exponentials as you want, and no one knows how to bound the mixing scale in terms of the L1 norm of the gradient. So all the current results that deal with the L1 norm of the gradient, you need to make extra structural assumptions on the vector field so that you can play some trick. So the first of these sort of structural assumptions is that you could imagine like that your vector field is built as a concatenation in time of vortices that sort of at each step they take a square and they rotate it by 90 degrees. So it's important that you actually rotate the square by a good amount. The 90 degrees isn't important, but if you were to, for instance, only rotate the square by some small epsilon, then your error is going to pile up on or your error is going to depend on epsilon, and you'll be in trouble. So maybe the key philosophical idea behind this is that the cost of a vortex, which is just the L1 norm of its gradient, is sort of proportional to the spatial scale that it operates on. So the proof has to use that pairing. And so under this assumption, Mahir Hadzik, Andreas Seeger, Charlie Smart, my advisor, and Brian Street were able to prove Bresson's conjecture under with this extra structural condition. So the special case. So I guess there's one thing that I forgot to mention, maybe even before Kripa and Deleuze's result, was Stefano Bianchini in 2006 considered a one-dimensional version of this problem and resolved it completely in one dimension. And so this result of Hadzik, Seeger, Smart, and Street is really using the same exact method as Bianchini, but just using the fact that when you're even in 2 dimensions, when your vector field is of this special form, you can't really do any more tricks than you could do in 1 dimension. So what's the idea? Well, the idea is exactly the same as the previous 2 proofs. So you come up with some energy functional. You show that at the initial time and at the final time it's very different, and then you bound the derivative in terms of the norm of your vector field. So in this case, we have some sort of multi-scale norm where I integrate over all, I wonder if I can draw, maybe not, maybe it's too risky. So I integrate over all sort of radii of balls, and so this r is like the radius of a ball, and this x is the center of the ball. And for each ball in the integral, I look at how far the fraction that ball is filled by our set A is. Oh, and this is a typo. That should be phi t of A. So it's the push forward by the flow map. So I look at how much of that ball is filled by A, and I compare that to perfect mixing, which would be 50-50. So what you can notice is that at each point x in space, this functional considers all the different scales. It considers all the scales r, and it weights them all equally. So a scale r is weighted the same as scale 2 times r. So maybe proof sketch is maybe too strong for how little detail I'm giving. But somehow the idea is that if you have a particular ball in this integral that you're interested in, and you have a particular vortex at the current time that the shear flow, or that the flow is composed of, then you really only have a strong contribution to this integral, or to the change in this integral, if the size of the vortex is comparable to the size of the ball that you're looking at. And so really, like, this is using that the cost and the spatial scale are linked. This is sort of the same as the same idea as the one-dimensional approach, because in one dimension you can't go around anywhere. You have to go straight through if you're going to travel between 2 points. So this is the first structural assumption. So the next one is so this is actually, I should mention, this is inspired by a counterexample in the previous result. So in this paper, they proved this result for the concatenation of vortices, and they show that their proof wouldn't work, or it can't possibly work. The energy blows up for shear flows instead of vortices. And so what's interesting is that shear flows look a lot like vortices, at least, or sorry, whoops. Oh wait, that's, oh, maybe this one. Okay. So now I'll talk about non-uniqueness right now. Okay, so they showed that for shear flows, this approach can't possibly work. So if you zoom in on a vortex, if you zoom in really close to the side, it looks like a shear flow. But this assumption that they're making is that whenever you run a vortex, you have to rotate all the way by 90 degrees. Whereas with shear flows, the result for shear flows allows you to switch back and forth between them as quickly as you want. So it's easier in some sense, because if you only look at shear flows, then you're not allowed to make sort of tiny changes in small spatial scales. Any change that you make has to at least stretch across the whole torus. So that's why the shear flow assumption makes the problem easier, but it's also a little harder because you're not forcing yourself to move a macroscopic distance. You can move a tiny difference and then oscillate to something else. So it's not really harder or easier. It's just sort of a separate assumption. So under this assumption, I can get the same rate as in Poisson's conjecture. So now I'll mention a little bit about the proof, which maybe the main idea of the proof is, again, sort of the same as all of the other proofs, which is you come up with some energy functional. You show that at the initial and final time it's very different, and you bound the derivative. So the computation is kind of messy in the continuous case. So I'm only going to consider a discrete version just to get the idea of the proof. And so imagine that I chop up my grid into sort of 2n by 2n squares. I want 2n because half of it is one color and half of it is the other color. And I imagine that 1 over n is like epsilon, like the scale that you're mixing to. So what are the allowed moves? Instead of just all shear flows, I'm going to consider something a little bit simpler, which is that at any time, you can just grab a contiguous bunch of rows or columns and shift them by 1 unit, either up or down or left or right. And so it seems maybe like this is a little bit more of an assumption than just shears, but it's not really, because if you have any sort of shear profile, so if I draw any shear profile that I want, I can split it up in some like layer cake decomposition and write it as a sum of these simple shears in a way that respects the norm. So really, this is the only thing you have to worry about by just splitting everything up in time. And so what's the energy? So far we've talked about 3 different energies. There is for the L infinity one, I track a particular pair of points. For the LP one, I track the optimal transport with a log cost. And for the vortex one, I track a multi-scale measure of energy. So here, our energy is going to be a lot closer to the Kripa-Dell'Ellis energy. And it's really inspired by Kripa and Dell'Ellis' energy, a lot more than the multi-scale energy. Because what we do is we sum over all of the points, all of the squares that started out on the left side of the torus. And we look at the distance to a square that started out on the right side of the torus, and we just take the log of that. So we just take the closest point that started out on the other side. So it's easy to see that at the initial time, this energy is pretty big, because most points that you sample, you have to travel a macroscopic distance to cross the center line. So there's n squared points, and the average distance is, well, I'm multiplying by n here so that I don't have a negative number in the log. So n squared points, and the average distance is n, so I get n squared log n at the initial time. And at the final time, it's a little bit, or I'm sorry, at the final time, it's just as easy to show that the distance is just the mixing scale at most. And so if the mixing scale is like 1 over n, then the energy is like n squared. And if you want, maybe it's nicer to just think of this as an average, so that really this is log epsilon and this is constant. So we showed that at the starting time and at the ending time, the energy takes very different values. And now I just want to show that after one move, the energy doesn't change too much. So what's the main idea for this? Well, take some point in your sum. So remember, the energy is just a sum over all points. So here, the blue squares are the ones that started out on the left, and the white squares are the ones that started out on the right. So I take some point, and I just look at the nearest square of a different color. And so if I'm taking the log of that distance, then the change that I'm going to observe is 1 over this distance from x to the nearest point of the other color, or 1 over the radius of this square, where the square is the largest square that's contained in the blue. So if you first just try to get a bound, then you know that if this term changes, then that must mean that the nearest point of the opposite color has to be across from the jump discontinuity. And so I get a sum of 1 over those distances, and I get n log n. And then if I translate the n's back into epsilons and recompute everything, this tells me the mixing scale is at least a constant. So that's useless. That doesn't help at all. On the other hand, our argument was kind of silly, because if you look at this point that we chose, when I apply the shear, the shortest distance doesn't change at all. Because this point here just moves up. It slides along the side, but it doesn't get any closer to x. So that tells me maybe there's something more clever I can do. And so instead of considering this x up here, I move 1 square down. And this is really the x that we should be worried about, because this point here is actually going to get closer. So we only need to worry about the x's, that the distance is going to change. Additionally, if I look at another point, for instance, the one right next to it, and I draw the largest bounding box that I can that stays inside of the blue, well, it can't contain this red box, because it can't contain the red box, because then it would contain this white square down here. And it can't be contained in the red box, because then it wouldn't border a white square. So the left edge has to move strictly to the right. So if I put that together, that tells me that the number of cells that matter, or by matter I mean the number of cells where their term in the sum changes, is at most the radius of the smallest box. And so what we get is that you're multiplying 1 over the radius times radius. So you get a contribution of constant for each row. And then if I sum over the rows, I get a contribution of n. And the fact that we lost the log n, before we had n log n, now we have n, means that if you trace everything back, you get the exponential result. So maybe that's all I want to say about this. I'll just say something very embarrassing is that This proof also doesn't work for the rotation, the vortex case. So can you handle vector fields that at each time are either vortices or shears? I don't know. That would be nice. I would be happy if you could tell me. And something basically the same as that is rotations without this 90-degree requirement. So that's all. Thanks for listening.
So again, we have time for questions, remarks, comments. Okay, everything seems quiet. So we thank again our speaker. So I think we have a coffee break now, and we start back in half an hour, I guess. So we end this afternoon section with I think the last lecture by Professor Albritton. Okay.
Thank you very much. So, okay, yeah, the last lecture, and I just want to say I've been really impressed with the level of the talks so far. Really impressive. So, so thank you all for I could tell also a lot of hard work went into them. Many of the graphics were outstanding, so thank you for that. Okay, so so now I need to tell you how to build this, how to really get these unstable self-similar solutions. Last time we said, okay, you take an unstable steady state and you just start rescaling it and you say, oh, that solves the forced equations. But a key point is that when you construct this object, it's unstable in self-similarity variables. So you have the steady state, which is unstable for the standard dynamics, and you start rescaling it. Is it going to be unstable for the self-similar dynamics? So that's a spectral perturbation argument. That's what we're going to do. And we're going to do a kind of toy version of that problem, which I hope you can take home with you. I want everyone to take home at least something from every lecture. The last lecture, I hope now you know you can derive Rayleigh stability equation. Maybe you can, and which is important. This one, I hope you can take home this perturbation argument. So, all right, so remember, we take our steady state, we artificially create this self-similar solution, and we know, because I accidentally turned it off for a second. Okay, so we know, so we have at least for 2D Euler, we have Wischig's unstable vortex. And so, for example, we know something like U bar, or we know something like this operator, U, maps to Leray projection, or is minus Leray projection, really, U dot grad U plus U dot grad U bar. We know that this linearized operator is unstable. And I want to show you how to, I want to show you how to make the self-similar problem kind of perturbative. So I'm going to use a variation on the self-similar coordinates. And there are other ways to do this, but we're going to use this way. Okay. So I'm going to use these similarity variables, where I've inserted an additional parameter kappa. So kappa is greater than 0. And I'm going to use this slightly adjusted ansatz, capital U of xi tau. Okay, for the force, there's a related ansatz. So when you write the PDE, it's going to have this power of, it's going to have this kappa factor here. And it's going to be minus kappa over 2, U, let me write 1 plus xi dot grad, capital U. By the way, if the letters look wavy, It's actually because the screen's wet, because I'm sweating. So let's put the Laplacian back in, and let's put the Laplacian in, and let's put the viscosity parameter back in, okay, this new. So then we have plus u dot grad u plus grad p is capital F. So when I make this slightly adjusted rescaling, I now have some parameters that I can play with. This is not exactly what we do in the paper, but there's also a way to see what we do in the paper as this. But now we have these parameters that we can play with. And in particular, we can make them small if we want. There's also this parameter here. But when you consider the linearized operator, all this parameter does is like chain. I mean, so when you linearize and when you take Laplace transform, all this does is modify your spectral parameter. So the linearized operator, you can think of it basically like, okay, minus kappa LSS capital U equals minus kappa over 2, 1 plus c dot grad U minus new Laplace capital U. And then we need this piece from, we need this Leray projected piece, u dot grad U plus u dot grad u bar. Now think to yourself, let me just say nu equals kappa for simplicity, and divide through by these factors. And when you divide through by these factors, I mean, this is just one way to think of it. Or maybe this is a better way to think of it. These factors are small. These factors are order kappa. This term, which is just the steady Euler linearized operator, is order 1. So these circled terms look perturbative. Okay, so these guys here, they look perturbative. And linearized steady Euler looks dominant. And we know that this operator is unstable. We know that there's an unstable eigenvalue for linearized steady Euler if you work everything out correctly. Or just saying that you know this piece of information. And so, therefore, you should be able to add on these small perturbations and get an unstable eigenvalue for linearized. It's linearized Navier-Stokes in self-similarity variables, right? So there are a few terms you're adding on. We want to treat them as perturbative. Okay, so this is how you go from unstable steady states to unstable self-similar solutions of the forced equation. Now, for 2D, we had the unstable vortex. That was a steady state. And then we can use this procedure to create the unstable self-similar solution and show that that's unstable, and then run some kind of unstable manifold argument. That was 2 lectures ago. That's what Vishik did, basically. By the way, when you do the unstable manifold construction for Euler, it's much more difficult because the equation is quasi-linear. Navier-Stokes is actually easier because the Laplacian's there, it can help you, it's semi-linear. So this Vishik construction, once you have the unstable vortex, you rescale it, you do the spectral perturbation argument, which shows that it's still unstable, and then you need to do this unstable manifold construction, which is harder because the equation is quasi-linear, but that's it. That's the procedure. So in 3D, if I want to do 3D Navier-Stokes, I still need an unstable steady state. I didn't explain how to do that yet. So for 3D, our unstable steady state is going to be an unstable vortex ring. It's going to be an unstable vortex ring. So let me explain that. So what you're going to do is you're going to take Vishik's unstable vortex. So that's really a function of, okay. So you'll take Vishek's unstable vortex. I'm going to call that U tilde because the vortex he constructs in his paper, it's not compactly supported, but you can make it compactly supported, like I mentioned last time. So it's called U tilde, the truncated unstable vortex. It's a vector field. It's a function of x and y. So this is like U tilde upper x, U tilde upper y, functions of x and y. That core is unstable. It's that there you have a radial, this radial vortex, it wants to break the symmetry. It wants to become not radial. It wants to become like m-fold symmetric for some m equals 2, say. So it wants to break the radial symmetry. What we're going to do is we're going to take that core, and we're going to take that unstable vortex, and it's going to serve as the core of a vortex ring. So the picture that you have in mind, or the picture you should have in mind, is, so we're going to axisymmetric variables. So axisymmetric variables, this is the r coordinate, this is the z coordinate. And you're going to take Vishek's unstable vortex, and it's going to serve as the core. Okay, so in reality, it's axisymmetric, so you think this thing is really, it's really a big ring, but schematically it's just like this. So this core here, this core is basically just this U tilde, Vishek's vortex. The radius of the core is like just order 1, but what we're going to do is we're going to put this core at a very large distance from the z-axis. Now, I'm going to explain why this is a good idea. But this is actually classical. So if you define the aspect ratio to be the diameter of the core divided by the length to the z-axis, then we'd say this vortex ring is small aspect ratio. Small aspect ratio. And these vortex rings were already considered by Kelvin and Helmholtz, and it's kind of classical stuff. I'm going to explain why it's a good idea in a second. But really, just to give you an idea of what's going on, the way we look at it is we take Vishek's vortex. Here it is. It's in 2D. It's a function of x and y. And you put it here. So now x becomes r and y becomes z. And it's really just spun at a very large distance like that. All right, so why do you do this? It's because key observation, which again was already known many years ago, and I learned this from papers of Vladimir Sverok and Thierry Gallet, who have been working on vortex rings. But basically, here it goes. So, axisymmetric Euler without swirl is approximately equal to 2D Euler when r is very big. In other words, at very large distances from the z-axis, the models are formally very close. So let me just write the models side by side. So first of all, for axisymmetric Euler, no swirl, that's U is UR. U is UR, a function of R and Z, ER, plus UZ, a function of R and Z, EZ. No swirl just means no E theta component. It's for the graduate students. So then the vorticity, which is the curl of U, the three-dimensional curl, is pure swirl. It's only in the E theta direction. And it makes sense to normalize it just because of the way some frames are organized. It makes sense to put this minus sign here, at least for what I'm about to say. And then, okay, the stream function, which solves Laplace, is also pure swirl. Okay, so you write the equation for omega theta. And here's the equation. So first of all, it's an advection equation. with stretching term, here's the stretching term. And the stretching term has 1 over r. Okay, so if you look r very big, just imagine that term is formally not there. So now I need to write the Biot-Savart law. So let me write, how do you recover the stream function? How do you recover the stream function from the vorticity? Now both the stream function and the vorticity are pure swirl. So here's the equation for recovering the stream function. Okay, and then how do you recover the velocity field? For the velocity field, u is minus dz psi theta er plus dr plus 1 over r psi theta ez. That's axisymmetric Euler, no swirl. So let's write 2D Euler. dt omega plus u dot grad omega. And okay, it's just like we were writing last lecture, Laplace psi equals omega. U is grad perp psi. So now we just stare and compare. So there are these additional terms which have 1 over these terms. They have 1 over r in them, like these terms. If you just ignore those terms, then 3D axisymmetric Euler is just 2D Euler, but x is like r and y is like z. All right? So what this gives you is it gives you a way to put 2D perturbatively into 3D. And that's what we want to do because we have a 2D unstable object, a 2D unstable steady state, and I want a 3D unstable steady state so I can run the rest of the scheme. So this is why you're going to construct this vortex ring small aspect ratio. And the construction really is, because we're working with forces everywhere, I don't actually have to worry about solving steady Euler at this point. I can solve steady Euler with a force. And this is probably the part of the proof where you could remove the force. And in fact, in 1970, Franco had some argument. Franco had, we've discovered this after we wrote everything. Franco has a kind of, he has also a kind of perturbative argument where you can prescribe the core of these vortex rings, but he does it without force. And you also, in that case, you let them travel with some speed. Okay, real vortex rings travel. But we just do the force variant here. So it makes sense to center your coordinates on the core of the ring. So what you really do is let my pen charge for a second. So what you really do is center the coordinates on the core of the ring. And then, okay, really. I can write but not erase. Well, that's all right. So you want to center the coordinates at the, so you really want to center at the core of the ring. So you say r is bigger than minus L. And okay, Z is in the real line. And so you're working in this kind of half space where like, here's your ring. Here's the core. But then here's R equals minus L. You're working in this kind of half space. And so in these equations will change ever so slightly. Wherever you have an R, you'll have an R plus L. You'll have an R plus L, and that makes the terms really look small. And all right, so the vortex ring, I'm sorry, technology is just not exactly. So I think we just relax for 30 seconds. I'm sorry. I think it's with the iPad. I don't think it's with your stuff. Yeah. So we'll just sweat for 20 more seconds. Okay, so you center your coordinates on the vortex, and I say u tilde sub L, a function of R and Z, it's literally equal to, so remember R is greater than minus L, it's literally equal to Wischig's vortex, so that's u tilde just evaluated at R and Z, but you need a small correction. The small correction is because when you take this 2D thing and just brutally stick it in to 3D, it's no longer divergence free in the physical variables. You make this correction VL, which is big O of 1 over L, and you can solve for it, and this corrects the divergence. So your vortex ring is really Wischig's core plus a small correction which makes it divergence free. And now what you need to do is you look at these two equations, and I know that if I linearize the second equation about Wischig's unstable vortex, I know it's unstable. And I need to linearize the first equation around my vertex ring. I need to show that linearized operator is unstable. In order to do that, I need to show the operators are close in some sense. This is the spectral perturbation argument. I have an unstable eigenvalue for one operator. I want to show that a nearby operator also has unstable eigenvalue. So we write, I'm just going to write the linearized operators for you, and then we're going to call it good, because then we're going to do the toy. The linearized operator, the proof is in the paper. It's a little bit hairy. Here's the linearized operator for 3D axisymmetric Euler around the ring. It's minus, I'm calling it L sub L. So first of all, there's an advection term. This is the term where the background, which is u tilde L, the ring, it advects the perturbation. So then you also have a term, which is where the perturbation, so you take the perturbation, omega, you calculate the velocity field, and this perturbation advects the background. Or rather, it tries to advect the background. So we usually give these terms names. This one is called minus m sub L omega. It's m because it's actually the unbounded term, which is making it the main term. This term here, which has the Biot-Savart law in it, we call it minus k sub L omega, because it's compact, because when you solve for the velocity field, you gain a derivative, and then you multiply by a compactly supported function. This operator is definitely compact. Okay, the last term comes from a vortex stretching term. Here it is. So Biot-Savart law, omega, the R component times omega tilde L, minus R plus L inverse, u tilde L R omega. This term also gets a name. We call this term minus S sub L omega because it's small. This term has an L in the denominator. It should just be small. The operator we're comparing, so this is 3D axisymmetric Euler no swirl, linearized around the ring. The operator we're comparing to is lin op around Wischig's vortex. And I'm calling that minus L infinity, because as you take L to infinity, formally it should converge to this. So this is a definition, this is a definition. This is u tilde dot grad omega. That's where Wischig's vortex tries to advect the perturbation. It advects the perturbation. And then u dot grad omega tilde. And these things get names. This is minus m infinity omega, and this is minus k infinity omega. Again, because m is the main term, it's the unbounded term, and these are unbounded operators. You need to set them up on closed, densely defined domains, and then k is compact. So, in fact, just because of the basic structure of these operators, you can say a lot. The basic structure is that you have one unbounded term, but it's antisymmetric. This one's okay. It's actually nearly antisymmetric, but for this one, for example, antisymmetric. Therefore, it has spectrum on the imaginary axis, and then you have a compact part which can create some eigenvalues. Those eigenvalues are the ones you're trying to control. Okay. So let me do the toy problem, which you can take home. In fact, there are two toy problems. So toy problems. So these are going to be toy problems just for 2D Euler. Okay. So here's 2D Euler. And let me linearize it. Go ahead and linearize it around some background U bar. And we consider this on the torus with 0 mean. So let me put it on T2 and mean 0. So this I'm going to call this thing a linearized operator. So this is minus L applied to omega. You normally say L. So operates from the domain of L, which is in L2 with 0 average to L2 0 average. And domain of L is simply it's simply all the omega in L2 with 0 average, such that U bar dot grad omega is also in L2, 0 average. Okay. So in other words, it's you just need to show that this main term, unbounded term, is in the function space. Then that's enough to be in the domain. Okay, so suppose L has an unstable eigenvalue. Unstable eigenvalue. And because of the structure, the antisymmetric plus compact structure, we know that, okay, it can have a central spectrum on the axis, but then everything else is just eigenvalues. So suppose it has an unstable eigenvalue like this one. Let's call that, I'm going to call that lambda infinity. Okay. So toy 1 is simply, suppose that you have a bunch of these steady states. I'm going to call them U bar sub k. And let's say that they converge to this little U bar in, I don't know, I'm just going to say Cm for every m. Just make the convergence really good. Okay. Then you want to show that Lk has an unstable eigenvalue. Unstable eigenvalue, lambda k, near lambda infinity, as long as k is sufficiently large. That's toy 1. There's lambda infinity, eigenvalue of the limiting operator, and I have a bunch of operators that are approximating it. I want to show that the eigenvalue doesn't move too much. Toy 2 is actually about adding viscosity. Okay, so show that linearized Navier-Stokes operator, L nu. So simply take that linearized operator, just add minus nu Laplace. So this linearized operator, okay, around U bar, has an unstable eigenvalue. Has an unstable eigenvalue near lambda infinity for nu sufficiently small. Okay. Questions on what we're trying to do? We're only going to do toy 1, and we're going to, but okay. I mean, we have enough time to prove toy 1. Toy 2, that's homework. Okay. So proposition. Let's try. All right. I can write but not erase. Oh my goodness.
From the room, they suggest to try this one.
But I need to connect it.
Yeah.
So I will need to do some connecting.
Perhaps it's simple. Too difficult.
Yeah, maybe it's too difficult. So
It's not the right moment.
yeah. I think it's not on you guys. It's on me. Okay. All right. Yeah. Tech people, how would you feel if I switched to the smart board? Could you help me switch to the board? Yeah. Sorry about this, but that's how.
These are good news. Natural intelligence is still faster than
Yeah.
artificial.
I wanted to write on the board anyway, so I'll be happy about this. Sir? This is great. This is great. Yeah. Do you have the pen? Oh, okay. Okay, great. Thank you very much. All right, so proposition. Yeah, toy one. Okay, so let lambda infinity be sufficiently large eval of L infinity, which I'm simply defining to be this L. That was the linearized operator around U bar. Okay, then for all k sufficiently large, okay. All right, let me, okay. In addition, okay. Also, let epsilon greater than 0, very small. Okay, then for all k, sufficiently large, but possibly depending on epsilon and the operators and various things. Okay, Lk has an unstable eigenvalue. Lambda k, and lambda k is epsilon close to lambda infinity. All right. Oh, thanks so much. So the picture, how do I scroll? Side. Okay, great. All right, so what you want to do is you want to define spectral projection. Okay. So here's the spectrum of the linearized operator L infinity. And again, you can have your central spectrum here, and you have some eigenvalue, lambda infinity. And you draw a contour around lambda infinity, and I'm going to call that contour vector C, this contour. So you have this contour, and you define spectral projection onto this part of the spectrum as, okay, so this is the spectral projection, pk onto this part of the spectrum, by integrating the resolvent, 1 over 2 pi I, integral around the contour C, the resolvent of this thing, d lambda. Okay, p infinity is non-trivial. That's because we know the limiting operator has an unstable eigenvalue in the contour. This pk will be non-trivial exactly when there's an unstable eigenvalue of the operator Lk in the contour. So yeah, this resolvent, I mean, it's the inverse of lambda minus Lk. Inverse. Defined whenever lambda is in the resolvent set. And so you want to, your goal is to show that pk is non-trivial. That's your goal. Because if you do that, then you know, I mean, oh, by the way, there's some small epsilon distance in here. If pk is non-trivial, you know there's an eigenvalue in there, and that's what you wanted to show. So in order to, what you can do, I mean, what you want to do is show that pk converges to p infinity. P infinity is non-trivial, then pk will have to be non-trivial. However, you need to be careful of the mode of convergence, because these operators, I mean, what are the operators? They're this is negative the operator. U bar, it's like this. These operators are all unbounded operators. They all have different domains. They're not going to converge in strong operator topology, okay? They're unbounded, and the unbounded terms are different. All right, so different unbounded terms. They're not going to converge in strong operator topology. However, in order to show that pk is non-trivial, it's enough to show that pkf converges to p infinity f for all f in all test functions. That'll be enough to show that pk is non-trivial. And this is what we're going to verify. So, okay, what do you actually want this? Or how are you actually going to show this? To show that those projections converge, projections are defined in terms of integrals of resolvents. So if I can show the resolvents converge, I'll get the projections that converge. So to show that resolvent lambda Lk converges, applied to f, converges to resolvent lambda L infinity f, okay, uniformly in lambda on the curve C. I just need that to pass the limit under the integral. And I need this for all f. Okay, so you break this up into two sublemmas. First lemma, okay, for all omega naught in L2 average, I'm going to show that just the resolvents of the main terms converge. Just going to start with the main terms. I met Anuj's eye. One person's paying attention, so we keep going. So, by the way, what's this mk? Mk is, so this term was minus mk times omega. The unbounded terms. The velocity fields are changing. So let's do a quick proof. We're going to utilize the Laplace transform characterization of resolvent. So this resolvent, mk omega naught is equal to the integral of e to the minus lambda t, e to the t mk, omega naught dt. By the way, this mk is simply an advection operator, okay? This semigroup is simply solving the transport equation. So this thing is e to the minus lambda t omega naught composed with the inverse flow map. So xk, xkt is flow corresponding to u bar k. Okay, and so if I want to show that these resolvents converge, all I need to do is pass to the limit in these flow maps. And okay, you can do that. But it depends on it depends on omega naught. The rate of convergence, all that stuff, that depends on omega naught. Okay, so you simply need to pass to the limit in these flow maps. You can do that. So now I have the resolvent corresponding to the main term converges. Let me try to get the resolvent of the whole operator. Okay. So this was just a sublemma, and so now let me do proof of Toit1. So I'm going to decompose my operator like this. Lambda minus mk minus kk. Okay, so far I've done nothing. My lk, remember, has a main term and a compact term. Next, I'm going to rewrite this as lambda minus mk applied to I minus r lambda mk, kk. So, okay, so far I haven't really done much. I just factored out this term. Okay, if I apply lambda here, I get lambda minus mk. When it hits the resolvent, then, okay, they're inverses, so I just get the kk term back. This thing here, I know that's invertible. And I know its resolvent converges. That was the last lemma. Okay. And its resolvent converges. So I really need to study this. If that's invertible and that resolvent converges, I'll be done just by composing the operators. So I need to study this. Luckily, kk is going to be compact, and that's going to help us out. Okay, so first of all, claim, first of all, claim I minus r lambda m infinity k infinity is invertible from L2 average to L2 average. Now, why might that be the case? If I plug k equals infinity here, then I know this term is invertible. So I know I'm in the resolvent set of L infinity. If you're in the resolvent set of L infinity, that'll be invertible. That'll be invertible. And therefore, this should be invertible. And one has to be a little careful about domains and stuff. A priori, actually, it gives you that this operator is invertible from the domain to the domain. And there's a subtle point there that will be explained in the notes. You need to use you need to say something of Fredholm operators. But let's just say that's at least very plausible. Okay, so now I know that the limit of this operator should be invertible. And so therefore, if I take k large enough, this should be invertible. But you have to be a little careful, because that resolvent didn't converge an operator norm. So if I want to study I minus r lambda mk applied to kk, this didn't converge an operator norm because it only converged against test functions. That's okay, because K is compact, so it can be well approximated by finite dimensional operators. This is compact, so can be well approximated by finite dimensional operators. If I plug in some finite dimensional operator, that thing will converge, because this resolvent only hits a finite dimensional subspace. So you need some kind of diagonal argument to show that this thing, this thing, MK, KK, actually does converge to this operator strongly in strong operator topology. And then that's enough to conclude, because that's invertible, so that's invertible. And then I went back up here. So that's invertible, and that's invertible. Therefore, the whole thing was invertible, and the resolvents are converging. And that's the end of the proof of the toy. So if you want to do the Navier-Stokes toy, what's different about that? What's different is in the proof that the unbounded parts of the operators converge. And here's where you really use that the operators are unstable. It's because this thing will no longer solve the transport equation. It'll solve advection diffusion. But that's OK, because you can take inviscid limit in advection diffusion, because it's a linear problem. You're not worried about boundary layers or some stuff. It's linear. So you can take inviscid limit in advection diffusion if you assume the data is regular enough, stuff like that. So OK, so this is the toy spectral perturbation argument. I'm sorry that technology was failing me, or maybe I failed it by not charging my pen. But I hope this makes sense. So just to conclude our discussion, I think that now we have a reasonable understanding of how these forced problems work. It would be really nice to move in the unforced problem direction. And for fluid equations, that all seems to be stuff where you can simulate it on the computer, and it looks pretty convincing that, OK, there's non-uniqueness. But you know, it's not so clear. So I think one interesting direction is to study, to try to study some simpler equations for which you really have a hope of handling unforced problems. That's been done in semi-linear heat equations, but I'm not fully up to date on literature there. But I think that there are some interesting directions there. And in particular, you want to get closer to like the ideal scenario of first blowup, then non-uniqueness. All this stuff was just, in some way, preparation for that. We started with rough initial data, and we showed non-uniqueness. But you want to work with models that first have blowup, then non-uniqueness. And some of these models exist: semi-linear heat equation, harmonic map heat flow. They have properties like this. But I think a lot more could be done. And OK. Thanks.
OK, so we have time for questions.
Thank you for your very nice talk. And so the non-uniqueness proved for Navier-Stokes equations, the initial data is 0. I'd like to ask, would it be possible for non-zero initial data for the non-uniqueness, also with force?
Also with force. Yeah. So in fact, so it is possible. And in fact, a group, Calvin Kaur and Changxing Miao and someone else, they took our gluing argument and they put subcritical initial data into it. Like, so you can still prove non-uniqueness if you make some initial data in LP, p greater than 3, And the force is same force. Because this thing is subcritical data, it's just perturbative. I mean, it doesn't, you know, they really, it's the gluing argument that we use for bounded domains. It really works kind of same. So it is possible to have non-zero data, and it's of moderate interest. I'm recorded, I guess. But yeah.
Thank you.
Yeah. No. Thanks for the question.
Other questions? Requests of more details? Foolproof, okay. Okay, so I think that we thank all the speakers of this afternoon. We thank our last speaker, and with him all the speakers of this afternoon session.